Planck's constant. In 1900, Max Planck was working on a problem that plagued physics. Classical theories couldn't explain how objects radiate heat. Desperate for a solution, he tried a mathematical trick. What if energy came in discrete packages, not continuous flows? He introduced a tiny constant, now called Planck's constant, into his equation. To his surprise, it worked perfectly, though he didn't fully understand why. This constant, symbolized by h, has a value of approximately 6.626 times 10 to the negative 34 joule-second. That's unimaginably small, but this tiny number is arguably the most important constant in all of quantum physics. It defines the fundamental granularity of our universe. Think of Planck's constant like the pixels on your TV screen. From a distance, the image looks smooth and continuous. Get close enough, though, and you see the individual pixels. Similarly, energy looks continuous in our everyday world. But zoom in far enough, and you'll discover that everything comes in tiny, indivisible packets, defined by Planck's constant. Here's why this matters. Planck's constant sets a fundamental limit on what we can know about the universe. It's the reason we can't measure a particle's position and momentum simultaneously with perfect precision. It's why electrons orbit atoms in specific energy levels rather than spiraling inward and collapsing. Without this constant, atoms couldn't exist, and neither could we. What's fascinating is how reluctant Planck himself was about his discovery. He called introducing energy quanta a purely formal assumption and an act of desperation. He expected his quantum hypothesis would eventually be replaced by something more intuitive. Instead, it became the foundation of a revolution. When Einstein endorsed Planck's constant to explain the photoelectric effect, and later when Niels Bohr used it to explain stable electron orbits in atoms, the quantum revolution was underway. This tiny number changed everything about how we understand reality. Planck's constant also appears in Heisenberg's uncertainty principle, in the equations for quantum tunneling, and in calculating the energy levels of quantum systems. It's even crucial for understanding black hole radiation, where Stephen Hawking showed that black holes aren't completely black, thanks to quantum effects scaled by, you guessed it, Planck's constant. Tonight, as you drift to sleep, imagine this tiny number, h, quietly governing the behavior of every particle in your bedroom, in your body, in the stars outside your window. The universe keeps perfect accounting of its energy, down to the smallest unit defined by Planck's constant, the quantum whisper. What if I told you that reality isn't what you think it is, that beneath the everyday world we experience lies a bizarre realm, where particles pop in and out of existence, where objects can be in two places at once, and where certainty dissolves into clouds of probability? This is the quantum realm, a whisper behind the shout of our classical world. The quantum whisper began around 1900 when physicists realized something strange about light. They expected it to behave like ocean waves, continuous and flowing. Instead, it acted like discrete packets of energy, what we now call photons. This discovery shattered centuries of understanding about how the universe worked. Imagine you're watching raindrops falling into a lake. Classical physics says the water should rise continuously as rain falls. But in the quantum world, the lake's level would jump up in tiny, discrete steps as each individual raindrop hits. These jumps are incredibly small, but they're there, the essence of quantum physics. What makes quantum physics so haunting, so strangely compelling, is how utterly it defies our intuition. We evolved to understand a world of tennis balls and trees, not electrons and atoms. The rules that govern the tiniest components of reality seem almost deliberately designed to make us uncomfortable. Yet this quantum whisper holds extraordinary power. It explains why atoms are stable, how stars shine, and why solid objects feel solid despite being mostly empty space. Your computer's transistors, MRI machines, and GPS satellite all work because we've learned to harness these bizarre quantum effects. As you drift towards sleep, consider this. Every atom in your body follows these strange quantum rules. The electrons in your cells exist as probability clouds, not definite points. The bonds between atoms in your DNA vibrate with quantum uncertainty. You are, at your most fundamental level, a collection of quantum possibilities temporarily arranged into the familiar pattern you call me. The quantum whisper reminds us that reality is far stranger and more wonderful than our limited senses suggest. Behind the solid world we navigate daily exists a shimmering foundation of probability and potential, whispering secrets that continue to astonish even the most brilliant mind. The Copenhagen interpretation. In the 1920s, a group of brilliant physicists gathered in Copenhagen, Denmark, to make sense of the strange new quantum world they were uncovering. Led by Niels Bohr and Werner Heisenberg, they developed what became known as the Copenhagen interpretation, the first and still most widely accepted way to understand quantum mechanics. The Copenhagen interpretation tells us something deeply unsettling. Quantum particles don't have definite properties until we measure them. Before measurement, they exist in a probabilistic haze called a superposition. It's not that we don't know what state the particle is in. It literally doesn't have a definite state. Only when we observe it does the particle decide which state to adopt. This is profoundly weird. Imagine flipping a coin. In our normal world, even while the coin is spinning in the air, it's either heads or tails. We just don't know which yet. But according to Copenhagen, a quantum coin is genuinely both head and tails simultaneously until someone looks at it. The Copenhagen interpretation also tells us that the act of measurement irreversibly collapses this probability wave into a single definite outcome. This collapse happens instantaneously and isn't caused by any known physical process. It just happens. This bothered Einstein tremendously, leading to his famous complaint that God does not play dice with the universe. Bohr responded, essentially telling Einstein to stop telling God what to do. The universe, it seemed, didn't care about human intuition or preference. What made the Copenhagen interpretation revolutionary was its pragmatism. Rather than speculating about what reality really is, it focused on what we could actually observe and measure. It declared questions about what quantum objects are doing when we're not looking at them as meaningless. As Bohr said, there is no quantum world. There is only an abstract quantum physical description. Critics argue that Copenhagen creates an artificial divide between the quantum world and our classical world, without explaining how one transitions to the other. It also gives special importance to measurement without clearly defining what counts as measurement. Nevertheless, the Copenhagen interpretation has endured for nearly a century because it works mathematically and gives correct experimental predictions, even if it leaves us philosophically unsatisfied. As you close your eyes tonight, ponder this. According to Copenhagen, the physical world only takes definite form when observed. When no one's looking, reality itself becomes blurry, indefinite, a cloud of possibilities waiting for consciousness to give it form. Schrödinger's peaceful cat. In 1935, physicist Erwin Schrödinger proposed a thought experiment that would become one of the most famous in all of science. Frustrated with what he saw as the absurdity of the Copenhagen interpretation, he devised a scenario to illustrate its paradoxical nature when applied to everyday objects. Imagine a cat placed in a sealed box with a deadly mechanism. Inside is a tiny bit of radioactive material with a 50% chance of decaying within an hour. If it decays, it triggers a hammer that breaks a vial of poison, killing the cat. If not, the cat lives. According to the Copenhagen interpretation, until someone opens the box to observe the outcome, the radioactive material exists in a superposition of both decayed and not decayed states. Consequently, the cat would exist in a superposition of both alive and dead state. This isn't about animal cruelty. No actual cats were harmed. It's about highlighting the seemingly absurd implications of quantum theory when scaled up to our everyday world. How could a living creature be simultaneously alive and dead? It sounds ridiculous, and that was exactly Schrödinger's point. He was criticizing, not endorsing, this interpretation of quantum mechanics. The beauty of this thought experiment is its simplicity and the profound questions it raises. It forces us to confront the boundary between the quantum world where particles routinely exist in multiple states simultaneously, and our classical world where cats are definitely either alive or dead, not both. Modern understanding has somewhat resolved this paradox through the process of quantum decoherence. The interaction of the quantum system with its environment, the box, air molecules, the cat, causes the quantum superposition to leak and resolve into a classical definite state extremely quickly. The cat never actually experiences being in a superposition. It's always definitely alive or definitely dead, even before we open the box. But Schrödinger's cat continues to prowl through our scientific imagination, representing the mysterious boundary between the quantum and classical realm. It reminds us that even after a century of quantum physics, we're still grappling with profound questions about the nature of reality. As you drift towards sleep, imagine that peaceful cat, definitely alive, definitely contentedly curled up, embodying not quantum weirdness, but the mystery and wonder of a universe that continues to surprise us with its depth and complexity. Schrödinger's cat, forever alive in our collective imagination, remains one of physics' most compelling paradoxes. Quantum tunneling. Imagine you're rolling a ball up a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. Simple, predictable, and consistent with everyday experience. But in the quantum world, something extraordinary happens. Sometimes the ball passes through the hill, emerging on the other side as if the hill weren't there at all. This seemingly impossible journey is called quantum tunneling. Quantum tunneling occurs because particles like electrons don't exist at precise points in space. Instead, they're described by probability waves that spread out across space. These waves don't abruptly stop at barriers. They gradually fade. If the barrier is thin enough, the probability wave extends to the other side, giving the particle a chance, sometimes a very small chance, but a real one, of being found there. It's as if you had a small probability of walking straight through a wall. In our everyday world, that probability is so astronomically small that it would never happen in the lifetime of the universe. But for tiny particles facing tiny barriers, it happens routinely. This isn't just theoretical. Quantum tunneling makes our modern world possible. Every transistor in your computer and smartphone relies on electrons tunneling through barriers that classical physics says they shouldn't be able to cross. Without tunneling, our digital age couldn't exist. But tunneling goes far beyond technology. It's essential for nuclear fusion in the sun's core. Protons in the sun don't have enough energy to overcome the electrostatic repulsion between them, yet they still manage to get close enough to fuse, releasing the energy that powers our planet. How? They tunnel past the barrier. Another example is radioactive decay. Alpha particles trapped inside unstable nuclei repeatedly slam against the energy barrier, keeping them imprisoned. Eventually, one tunnels out, resulting in radioactive decay. The rate of tunneling determines the half-life of radioactive material. Quantum tunneling even plays a role in biological processes, including photosynthesis and some enzyme action. There's emerging evidence that some enzymes use tunneling to transfer hydrogen atoms, making biological reactions more efficient. What makes tunneling so fascinating is how it defies our intuition. It's like finding out gravity occasionally works sideways. It reminds us that the rules governing the subatomic world are profoundly different from those we experience. Tonight, as you lie in bed, consider that the electrons in the atoms of your blanket are constantly attempting to tunnel away. Most fail. Probability waves are mostly confined, but the universe is constantly calculating these probabilities, creating the subtle quantum dance that underlies our seemingly solid reality. The double-slit experiment. If I had to nominate one experiment that captures the mysterious heart of quantum mechanics, it would be the double-slit experiment. It's deceptively simple, yet its results are so bizarre that physicist Richard Feynman claimed it contains the only mystery of quantum mechanics. The experiment begins straightforwardly. Imagine a wall with two narrow slits and a screen behind it. If you shoot particles, let's say electrons, one at a time through these slits, what pattern would you expect to see building up on the screen? Common sense suggests two bands, right? Each electron goes through either the left slit or the right slit and hits the screen directly behind. But that's not what happens. Instead, the electrons create a pattern of multiple alternating light and dark bands, an interference pattern. This is what waves do when they pass through two openings and then overlap, creating regions where they enhance or cancel each other out. But remember, we're firing individual electrons, one at a time. How can a single electron interfere with itself? It's as if each electron somehow goes through both slits simultaneously. Even stranger, if we try to watch which slit each electron goes through, the interference pattern disappears. Just by observing, we change the outcome. The electrons start behaving like ordinary particles, creating just two bands on the screen. This experiment reveals something profound. Unobserved particles seem to behave like waves of probability, existing in multiple places simultaneously. But when observed, they snap into definite particle-like behavior with specific positions. It's like reality itself is undecided until someone looks at it. Scientists have run versions of this experiment with electrons, photons, atoms, and even large molecules like buckyballs containing 60 carbon atoms. All show the same bizarre wave-particle duality. What I find most fascinating is how this simple experiment forces us to confront the limits of our intuition. We evolved to understand the macroscopic world of everyday objects, not the quantum realm. Our brains simply aren't wired to grasp quantum reality intuitively. There's something humbling about this. The double-slit experiment reminds us that the universe isn't obligated to make sense to human mind. Reality is what it is, regardless of whether we find it intuitive or comfortable. As you drift towards sleep, picture those silent electrons passing through both slits simultaneously, existing as probability waves until observed, revealing a world far stranger and more wonderful than our ancestors could have imagined. Wave function collapse. At the heart of quantum mechanics lies a mathematical entity called the wave function, an abstract mathematical expression that contains all the information about a quantum system. Rather than telling us exactly where a particle is or how fast it's moving, the wave function gives us probabilities. It's like a forecast telling us where we're likely to find the particle if we look for it. But something strange happens when we actually measure a quantum system. The spread-out probabilistic wave function seems to instantly collapse into a definite state. Before measurement, an electron might exist as a cloud of probability, potentially located in multiple places simultaneously. After measurement, it suddenly appears in just one specific location. This transition from many potential states to one actual state is called wave function collapse, and it's one of the most puzzling aspects of quantum mechanics. What's particularly strange is that there's no clear physical mechanism causing this collapse. It just happens when a measurement occurs. Think about flipping a coin. While it's spinning in the air, the wave function would represent the probability of getting heads or tails. But in the quantum version, the coin isn't just unknown. It's genuinely both heads and tails until someone looks at it. The act of observation collapses the wave function, forcing reality to choose one outcome. Scientists have debated for decades about what's actually happening during wave function collapse. Is it a real physical process? Is it just a change in our knowledge about the system? Does consciousness somehow play a role in collapsing the wave function, as some have controversially suggested? Some interpretations of quantum mechanics, like the many worlds interpretation, avoid wave function collapse entirely. They suggest the wave function never actually collapses. Instead, each possible outcome happens in a different branch of reality, creating parallel universes with each measurement. Wave function collapse connects to larger philosophical questions about reality. Is the world fundamentally probabilistic or deterministic? Does objective reality exist independent of observation? The mathematics works perfectly, but what it all means remains contentious. What's clear is that wave function collapse marks the boundary between the weird quantum world and our familiar classical world. It's where possibility transforms into actuality, where the multiple potential states of quantum systems resolve into the single reality we experience. As you lie in bed tonight, consider this. Perhaps the wave function of all possible dreams you might have is about to collapse into the specific dream you'll actually experience, guided by the mysterious quantum process that still puzzles the greatest scientific mind, quantum entanglement. Einstein called it spooky action at a distance, and it might be the strangest phenomenon in all of quantum mechanics. Quantum entanglement occurs when two or more particles become connected in such a way that the quantum state of each particle cannot be described independently of the others, no matter how far apart they are. Imagine two coins that are somehow magically linked. If one shows heads, the other instantly shows tails, even if they're on opposite sides of the universe. That's roughly how entanglement works, except with quantum properties like spin or polarization. The spooky part is that this correlation happens instantaneously, faster than light could travel between the particles. When you measure one entangled particle, its partner instantly knows and adopts the corresponding state. This seems to violate Einstein's theory of relativity, which states that nothing, including information, can travel faster than light. Einstein, Podolsky, and Rosen, EPR, suggested in 1935 that quantum mechanics must be incomplete, as this apparent faster-than-light communication seemed impossible. They believed there must be hidden variables, some pre-existing shared properties that determined the outcomes but remained unknown to us. 30 years later, physicist John Bell developed a mathematical framework to test this idea. Subsequent experiments, particularly those by Alain Aspect in the 1980s, showed that entanglement is real. There are no hidden variables. The universe really does have this bizarre non-local connection built into its fabric. But here's the catch. Despite this instant correlation, entanglement can't be used to transmit information faster than light. When you measure your entangled particle, you get a random result. The only special thing is that your distant partner will get a correlated result. You'd need to communicate the result of your measurement through conventional means, limited by light speed, for your partner to make sense of their measurement. Today, quantum entanglement isn't just a theoretical curiosity. It's the foundation for emerging technologies like quantum computing, quantum cryptography, and quantum teleportation. Scientists routinely create entangled particles in labs, and in 2017, Chinese scientists demonstrated entanglement between particles separated by 1,200 kilometers. Entanglement reveals a profound truth. Our universe isn't made of separate objects that occasionally interact. At the quantum level, reality is fundamentally interconnected in ways that transcend space itself. As you drift towards sleep, consider this. The particles in your body once interacted with particles throughout the cosmos. Some might remain subtly entangled with distant matter, connecting you to the fabric of the universe in ways beyond our everyday perception. Heisenberg's uncertainty principle. In 1927, a young German physicist named Werner Heisenberg discovered something profound about the fabric of reality. He realized that there are pairs of properties in quantum systems that cannot both be precisely known simultaneously. The more accurately you measure one property, the less accurately you can know the other. This fundamental limit on knowledge is known as Heisenberg's uncertainty principle. The classic example involves position and momentum, which is mass times velocity. The better you know where a particle is, the less you can know about how fast it's moving, and vice versa. This isn't due to poor measuring equipment or technique. It's built into the nature of reality itself. Mathematically, the principle states that the product of the uncertainties in position, dx, and momentum, dp, can never be smaller than Planck's constant divided by 2pi. dx times dp greater than or equal to h bar divided by 2. To grasp why this happens, remember that quantum particles have wave-like properties. A perfectly defined position would require a wave that's infinitely narrow, a spike at one location. But such a wave is made up of an infinite range of wavelengths, which means an infinite range of momentums. Conversely, a particle with perfectly defined momentum would have a single wavelength extending infinitely through space, meaning its position would be completely undefined. This uncertainty is why atoms don't collapse. Classical physics suggests that electrons should spiral into the nucleus, but the uncertainty principle prevents this. If an electron were confined too closely to the nucleus, its position uncertainty would be very small, which means its momentum uncertainty would be enormous. This uncertainty keeps electrons in their orbital clouds rather than crashing into the nucleus. Uncertainty also explains quantum tunneling, where particles pass through barriers they shouldn't have enough energy to overcome. Since a particle's energy can't be known precisely, there's always a small probability it will have enough energy to pass through. People often misinterpret Heisenberg's principle, thinking it merely states that the act of measurement disturbs what's being measured. While measurement disturbance is real, the uncertainty principle is deeper. It states that certain pairs of properties cannot simultaneously have precise values, regardless of measurement. Heisenberg's discovery fundamentally changed our understanding of reality. It revealed that the universe isn't deterministic at its core. There's an inherent fuzziness to nature. As Heisenberg himself put it, the more precisely the position is determined, the less precisely the momentum is known in this instant, and vice versa. Tonight, as you relax in bed, embrace the uncertainty in your own life. Like quantum particles, perhaps the most beautiful aspects of existence emerge not from perfect certainty, but from the dynamic dance of possibility. The observer effect. One of the most profound and philosophically challenging aspects of quantum mechanics is the observer effect. The idea that the mere act of observing a quantum system inevitably changes it. This might sound mystical, but it's a real, experimentally verified phenomenon with far-reaching implications for our understanding of reality. Unlike the uncertainty principle, which states an inherent limit to what can be known, the observer effect concerns how measurement physically affects what's being measured. At the quantum level, there's no way to observe something without interacting with it in some way. Think about how you see objects. Light bounces off them and into your eyes. For large objects, this light doesn't noticeably affect them. But for quantum particles, even a single photon of light carries enough energy to significantly alter the particle's behavior. The classic example is the double-slit experiment. When electrons pass through two slits unobserved, they create an interference pattern suggesting they went through both slits simultaneously as waves. But when we place detectors to observe which slit each electron passes through, the interference pattern disappears, and the electrons behave like particles going through one slit or the other. Crucially, observation doesn't require a conscious human observer. Any interaction that could reveal definite information about a quantum system, whether it's with a detector, light photon, or air molecule, constitutes an observation. The quantum system becomes entangled with whatever it interacts with, causing the wave-like behavior to decohere into particle-like behavior. Nevertheless, the observer effect raises profound philosophical questions. If reality behaves differently when observed versus unobserved, what does this tell us about the nature of reality itself? Is there an objective reality independent of observation? Or does reality, in some sense, require observation to take definite form? Physicist John Wheeler proposed a thought experiment called the delayed choice quantum eraser that seems to suggest the act of observation in the present can affect how a particle behaved in the past. This has led some to speculate that consciousness might play a special role in quantum mechanics. Though most physicists reject this interpretation, the observer effect reminds us that at the quantum level, there's no clear separation between the observer and the observed. We can't stand apart from nature and observe it without affecting it. We're participants in reality, not just spectators. As you close your eyes tonight, consider this. Even the photons that bounced off these words and into your eyes changed the quantum states of the atoms in your screen. In the quantum world, nothing can be observed without being changed. A humbling reminder of our intimate connection with the universe. Quantum superposition. At the heart of quantum mechanics lies a concept so strange It seems to defy logic. Quantum superposition. It's the idea that quantum systems can exist in multiple states simultaneously until they're measured, at which point they collapse into a single definite state. To understand superposition, forget everything common sense tells you about how objects behave. In our everyday experience, a coin is either heads or tails. A light switch is either on or off, and you're either reading this or not reading this. But in the quantum world, a particle can be in a state that's literally both heads and tails until someone looks at it. Superposition isn't just a theoretical concept. It's been demonstrated in countless experiments. Perhaps the most famous is the double-slit experiment, where individual electrons create an interference pattern as if each electron passes through both slits simultaneously, interfering with itself like a wave. Mathematically, superposition is represented as a sum of different possible states, each with a certain probability. For example, an electron's spin might be in a superposition of up and down, expressed as psi I up plus b down, where A and B are probability amplitude. What makes superposition so counterintuitive is that these aren't just probabilities reflecting our ignorance. The particle genuinely exists in multiple states simultaneously. It's not like a spinning coin, where it's definitely either heads or tails, and we just don't know which yet. In quantum superposition, reality itself is indeterminate until measurement forces it to commit to a specific state. Superposition is the key to quantum computing's potential power. While classical computers process bits that are either 0 or 1, quantum computers use qubits that can exist in superpositions of 0 and 1 simultaneously. This allows quantum computers to explore multiple solutions to a problem in parallel, potentially solving certain problems exponentially faster than classical computers. Schrödinger's famous cat thought experiment was designed to highlight the absurdity of applying superposition to everyday objects. If quantum particles can exist in superposition, then a cat connected to a quantum event could theoretically be both alive and dead simultaneously, a notion that seems ridiculous for a macroscopic object like a cat. So why don't we observe superpositions in everyday life? A process called quantum decoherence causes quantum systems to lose their superposition when they interact with their environment. The more particles involved, the faster decoherence happens, which is why quantum effects are typically only observable at the atomic and subatomic scales. As you drift towards sleep, imagine yourself in a quantum superposition of both sleeping and waking, existing in multiple states simultaneously, embracing the strange wonder of a universe where possibility is woven into the very fabric of reality. Quantum non-locality. Quantum non-locality might be the most profound discovery in all of physics, a property so strange that Einstein famously called it spooky action at a distance. It reveals that the universe isn't made of separate, independent objects, but is instead an interconnected whole where distance itself might be an illusion. Non-locality refers to the fact that quantum particles that have interacted can remain connected, entangled, in such a way that an action performed on one instantly affects the other, regardless of the distance separating them. Measure the spin of one entangled electron as up, and its partner instantly becomes down, even if they're at opposite ends of the galaxy. What makes this truly spooky is that this correlation happens instantaneously, faster than light could travel between the particles. This seems to violate Einstein's theory of relativity, which states that nothing, including information, can travel faster than light. Einstein believed that quantum mechanics must be incomplete, suggesting there must be hidden variables, predetermined properties that both particles carried from their initial interaction. In 1964, physicist John Bell developed an ingenious test, now known as Bell's inequality, to settle the debate. Subsequent experiments have consistently violated Bell's inequality, confirming that quantum non-locality is real. There are no hidden variables. But here's where it gets subtle. Despite this instant correlation between entangled particles, non-locality can't be used to transmit information faster than light. When you measure your entangled particle, you get a random result. The only special thing is that when your distant partner measures their particle, they get a correlated result. You'd need to communicate your result through conventional means, limited by light speed, for your partner to recognize the correlation. Non-locality forces us to reconsider some of our most basic assumptions about reality. It suggests that space itself might be an emergent property rather than a fundamental aspect of reality. At the deepest level, there might not be any distance between entangled particles. They remain connected in ways that transcend our conventional understanding of space. Some physicists have suggested that quantum non-locality points to a deeper level of reality, a unified field or implicate order from which our familiar world emerges. Others propose that entangled particles might be connected through higher dimensions or wormholes in spacetime. Whatever the ultimate explanation, quantum non-locality reveals that reality is not what it seems. The separate, independent objects we perceive in everyday life give way, at the quantum level, to an indivisible whole, a universe where everything is connected in ways that defy our intuitions about space and time. As you fall asleep tonight, consider that the particles in your body remain entangled with distant matter throughout the cosmos, connecting you to the universe in ways that transcend space itself. The quantum vacuum. Imagine the emptiest place you can think of, deep space, far from any stars or planets. You might picture a perfect void, absolute nothingness, but quantum physics tells us something astonishing. There's no such thing as empty space. What we call a vacuum is actually teeming with activity, a roiling sea of virtual particles and energy fluctuations. This is the quantum vacuum, perhaps the most misleading nothing in all of science. Classical physics views a vacuum as truly empty, but according to quantum field theory, empty space is filled with field, the electromagnetic field, electron field, quark fields, and others. These fields are never truly at rest, even at their lowest energy state. Instead, they fluctuate constantly due to the uncertainty principle, which states that a field's energy and time cannot both be precisely defined simultaneously. These fluctuations manifest as pairs of virtual particles that briefly pop into existence before annihilating each other and disappearing. These aren't real particles in the conventional sense. They exist for such incredibly short periods that they can't be directly observed. They're like quantum credit card debt. The universe borrows energy to create these particles, but must quickly pay it back to balance the books. Despite their fleeting nature, these virtual particles have measurable effects. One example is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum are drawn together. This happens because fewer virtual particles can fit between the plates than outside them, creating a kind of quantum pressure difference. The quantum vacuum also explains the Lamb shift, a small difference in energy levels of hydrogen atoms that classical theory couldn't account for. Virtual particles temporarily distort the electron's environment, shifting its energy slightly. Perhaps most dramatically, the quantum vacuum is responsible for Hawking radiation. Near a black hole's event horizon, virtual particle pairs can be torn apart if one falls in while the other escapes. The escaping particle becomes real, carrying away energy, causing the black hole to gradually evaporate. Some cosmologists propose that the entire universe might have emerged from a quantum fluctuation in the vacuum, literally something from nothing. Others suggest that vacuum energy, or dark energy, might be driving the accelerating expansion of the universe. The quantum vacuum challenges our most basic intuitions about reality. Emptiness isn't empty. Nothing is something. Even the void between stars is alive with possibility, as virtual particles flicker in and out of existence like quantum fireflies. Tonight, as you lie in bed, remember that the seemingly empty space around you is actually a dynamic, energetic field of quantum possibility. The void breathes with virtual potential, an eternal dance of creation and annihilation happening in every cubic centimeter of nothing. Quantum field theory. Quantum field theory, QFT, might be the most successful theory in the history of physics. It's the framework that unites quantum mechanics with special relativity and provides our deepest understanding of how particles and forces interact. Rather than viewing particles as tiny billiard balls, QFT sees them as excitations in underlying fields that permeate all of space. Imagine a field as a vast, invisible fabric stretching across the universe. Each type of particle, electrons, photons, quarks, has its own corresponding field. When these fields oscillate or ripple in certain ways, we detect these disturbances as particles. It's similar to how ocean waves are disturbances in the water, not separate objects that move through it. This shift in perspective from particles to fields was revolutionary. In classical physics, particles and fields were distinct concepts. Electromagnetic fields existed, and so did electrons, as fundamentally different things. QFT unifies these concepts, showing that particles are just localized excitations of their underlying fields. QFT explains something that earlier quantum mechanics couldn't: how particles can be created and destroyed. In processes like pair production, energy can convert into matter as new ripples form in quantum fields. Similarly, when particles annihilate, their energy returns to the fields. This explains everything from radioactive decay to the creation of particles in colliders. One of QFT's most profound insights is that empty space isn't empty. Quantum fields are always active, with virtual particles constantly popping in and out of existence due to energy fluctuation. This vacuum energy has measurable effect, like the Casimir force between closely spaced plates. QFT also explains how forces work. In the quantum world, forces are transmitted by special particles called bosons. Photons carry the electromagnetic force, gluons carry the strong nuclear force, and W and Z bosons carry the weak nuclear force. When two electrons repel each other, they're actually exchanging photons, like people in boats throwing balls back and forth, causing the boats to move apart. The crowning achievement of QFT is the Standard Model, which describes all known particles and 3 of the 4 fundamental forces. It has successfully predicted particles like the Higgs boson before they were discovered, and its calculations match experiments with astonishing precision. Despite its success, QFT isn't complete. It struggles to incorporate gravity, and questions remain about the nature of dark matter, dark energy, and why the universe contains more matter than antimatter. These mysteries hint at deeper physics beyond quantum field theory. As you drift towards sleep, consider that you're not a collection of separate particles, but a complex pattern of interacting quantum fields, temporary ripples in the cosmic ocean that forms the foundation of reality itself. Virtual particles. If I told you that empty space is actually full of particles constantly popping into and out of existence, you might think I was describing some mystical or spiritual concept. Yet this strange idea, virtual particles, is a cornerstone of modern physics, supported by mountains of experimental evidence. Virtual particles are temporary quantum fluctuations that appear seemingly out of nowhere and then disappear back into the quantum vacuum. They're called virtual because they can't be directly observed and don't last long enough to be considered real particles. Think of them as the universe borrowing energy to briefly create particles, then quickly paying back that energy when the particles annihilate each other. How is this possible? Heisenberg's uncertainty principle tells us that energy and time are complementary variables. The more precisely you know one, the less precisely you can know the other. This means that for very short time intervals, the energy of a system can fluctuate significantly, allowing particle-antiparticle pairs to momentarily exist before they recombine and vanish. These ephemeral particles aren't just a theoretical curiosity. They have real, measurable effects. The Lamb shift, a small difference in energy levels of hydrogen atoms, occurs because virtual particles temporarily distort the electron's environment. The Casimir effect, where closely spaced metal plates are drawn together in a vacuum, happens because fewer virtual particles can fit between the plates than outside them. Virtual particles also explain how forces forces work at the quantum level. When electrons repel each other, they're actually exchanging virtual photons. The strong nuclear force between quarks involves the exchange of virtual gluons. Even gravity might involve virtual particles called gravitons, though we haven't confirmed this experimentally. Perhaps most dramatically, virtual particles are responsible for Hawking radiation. Near a black hole's event horizon, virtual particle pairs can be separated if one falls in while the other escapes. The escaping particle becomes real, carrying away energy and causing the black hole to gradually evaporate. The existence of virtual particles challenges our intuitive understanding of nothing. The vacuum isn't empty, but a seething quantum foam where particles continually flicker in and out of existence. This has profound implications. Some cosmologists propose that our entire universe might have begun as a quantum fluctuation, a virtual particle that somehow became permanent. As you drift towards sleep, imagine the space around you alive with invisible activity, virtual electrons, photons, and quarks dancing briefly into existence before disappearing, a constant effervescence of quantum possibility occurring in every cubic centimeter of what we mistakenly call empty space. The Casimir effect. Imagine placing two uncharged metal plates in a vacuum, perfectly parallel and extremely close together, just a few nanometers apart. Classical physics would predict nothing happened. With no charge or mass between them, there should be no force. Yet experimentally, these plates are pulled together by a mysterious force. This is the Casimir effect, one of the strangest confirmations that the quantum vacuum is far from empty. First predicted by Dutch physicist Hendrik Casimir in 1948 and conclusively measured in 1997, this effect emerges from the behavior of virtual particles in the quantum vacuum. To understand it, picture the quantum vacuum as a sea of virtual particles constantly popping in and out of existence. These virtual particles include virtual photons of all possible wavelengths. When you place the plates close together, something interesting happens. Virtual photons can only exist between the plates if their wavelengths fit perfectly, like standing waves on a guitar string. Longer wavelengths simply won't fit in the narrow gap. This creates an imbalance. Fewer types of virtual photons can exist between the plates than outside them. With more virtual photons pushing from outside than from inside, the plates experience a net force pushing them together. It's as if the empty space outside the plates is fuller than the empty space between them. This force is tiny, about 1/30,000th of atmospheric pressure for plates 10 nanometers apart, but unmistakably real. What makes the Casimir effect so profound is that it's one of the few directly measurable consequences of vacuum fluctuations. It proves that empty space has energy and structure, that nothing is actually something. Beyond its theoretical importance, the Casimir effect has practical implications. In nanotechnology, where components are incredibly small, the Casimir force can cause tiny mechanical parts to stick together, an effect called stiction. Engineers designing nanomachines must account for this quantum mechanical effect. The Casimir effect also appears in surprising places in nature. Some geckos can stick to walls partly due to Casimir forces between the tiny hairs on their feet and the wall surface. Scientists are exploring how these quantum forces might be harnessed for everything from frictionless bearings to new types of adhesives. Some researchers have even proposed using the Casimir effect to extract energy from the vacuum, though this remains highly speculative. Others study how the effect might be reversed or manipulated by using specially designed materials. As you contemplate sleep tonight, consider that the seemingly empty space around you has structure and energy, that even perfect nothingness exerts forces on the physical world. The Casimir effect reminds us that reality is stranger and richer than our intuition suggests, with quantum effects quietly shaping the world we experience. Quantum decoherence. Why don't we see cats in superpositions of a live and dead state? Why don't baseballs tunnel through walls? Why does the weird quantum world give way to the familiar classical world of our everyday experience? The answer lies in a process called quantum decoherence. decoherent, the mechanism by which quantum systems lose their delicate, wave-like properties as they interact with their environment. To understand decoherence, first recall that quantum systems can exist in superpositions, multiple states simultaneously. An electron can be in a superposition of spin-up and spin-down, existing in both states at once until measured. These states aren't just alternative possibilities. They can interfere with each other like waves, creating distinctive quantum patterns. But this wave-like behavior is incredibly fragile. When a quantum system interacts with its environment, with air molecules, light photons, or other particles, information about its quantum state leaks out into the environment. This process effectively measures the system continuously, causing its superposition to rapidly collapse. Imagine dropping a pebble into a still pond, creating perfect circular ripples. Now imagine dropping that same pebble into a choppy ocean during a storm. The delicate wave pattern would be lost among the chaotic background waves. Similarly, quantum coherence, the delicate wave-like pattern of a superposition, gets lost in the noisy ocean of environmental interaction. Decoherence explains why quantum effects are typically only observable in carefully controlled laboratory conditions. Scientists must isolate quantum systems from their environment using ultra-high vacuums, extreme cold, near absolute zero, or other techniques to preserve their quantum nature. The larger an object is, the faster decoherence happens. A single electron might maintain its quantum coherence for a relatively long time. A molecule made of dozens of atoms might stay coherent for just microseconds, and a macroscopic object like a cat interacts with countless air molecules, photons, and other particles, causing virtually instantaneous decoherence. Importantly, decoherence doesn't solve the measurement problem in quantum mechanics. It doesn't tell us why measurement yields specific outcomes. Rather, it explains why we don't see quantum superpositions in everyday life. Understanding decoherence is crucial for developing quantum technologies. Quantum computers, for instance, rely on maintaining quantum coherence in their qubits. Engineers must fight decoherence through error correction techniques and by isolating quantum systems from environmental noise. Decoherence also sheds light on fundamental questions about the quantum classical boundary. Rather than a sharp dividing line, there's a continuous spectrum from quantum to classical behavior, with decoherence acting as the bridge between these realms. As you fall asleep tonight, consider that the seemingly solid, definite world around you emerges from a quantum realm of probabilities and possibilities, a blurry quantum picture that sharpens into focus through the relentless process of decoherence. As quantum systems interact with their environment millions upon millions of times each second, many worlds interpretation. Imagine every decision you've ever made, every coin you've ever flipped, every quantum event in history, each one splitting reality into separate branches, creating a vast, ever-expanding multiverse of possibilities. This is the essence of the many worlds interpretation, MWI, one of the most mind-bending attempts to make sense of quantum mechanics. Proposed by physicist Hugh Everett III in 1957, the many worlds interpretation offers a radical solution to the measurement problem in quantum mechanics. Instead of wave functions mysteriously collapsing when measured, MWI suggests something far stranger. The wave function never collapses at all. Rather, it continues to evolve according to the Schrödinger equation, with all possible outcomes occurring in different worlds or branches of reality. When you measure a quantum system, say an electron that's in a superposition of spin-up and spin-down states, the universe splits into two branches. In one branch, you observe spin-up. In the other, you observe spin-down. Both outcomes happen, just in different branches of reality that can no longer interact with each other. This perspective eliminates the need for wave function collapse, creating a more mathematically elegant theory. It also removes the special role of the observer in quantum mechanics. There's nothing special about consciousness or measurement that causes reality to choose one outcome over another. All possibilities happen. We just experience one branch. Despite its elegance, many worlds remains controversial. For one thing, it's extraordinarily extravagant, positing an infinite or near-infinite number of parallel universes, most of which we can never detect. Critics argue this violates Occam's razor, which favors simpler explanation. Others question whether MWI is even testable. If parallel branches can never interact, how could we ever prove their existence? Some physicists argue that MWI makes the same empirical predictions as other interpretations, making it a philosophical preference rather than a scientific theory. Proponents counter that the lack of wave function collapse makes MWI more consistent with quantum field theory and relativity. They also point out that many established scientific concepts, from electrons to black holes, were initially considered unobservable. MWI has inspired numerous science fiction stories, from Philip K. Dick's The Man in the High Castle to the television series Rick and Morty. But unlike fictional portrayals, the worlds in MWI aren't spatial regions you could travel between. They're separate branches of the universal wave function that can no longer interact. Whether you find it compelling or absurd, the many worlds interpretation reminds us that quantum mechanics forces us to reconsider our most basic assumptions about reality. It suggests that existence might be far stranger and more vast than our everyday experience indicates, a multiverse of possibilities, of which we experience only one thin slice. As you drift towards sleep tonight, perhaps in another branch of reality, another version of you chose to read something entirely different. The pilot wave theory. What if quantum particles were just ordinary objects guided by an invisible wave? This simple yet profound idea forms the basis of pilot wave theory, also called Bohmian mechanics or de Broglie-Bohm theory, an alternative interpretation of quantum mechanics that challenges the mainstream Copenhagen view with a surprisingly intuitive approach. First proposed by Louis de Broglie in 1927 and later expanded by David Bohm in the 1950s, pilot wave theory suggests that quantum particles always have definite positions and trajectories, just like classical objects. The key difference is that these particles are guided by a real physical wave, the pilot wave or quantum potential, that evolves according to Schrödinger's equation. This pilot wave exists in configuration space, a mathematical space that represents all possible positions of all particles in the system. It knows about the entire experimental setup and guides particles accordingly, producing the interference patterns we observe in experiments like the double-slit test. The theory's appeal lies in its deterministic nature. Unlike the probabilistic Copenhagen interpretation, where particles don't have definite properties until measured, pilot wave theory returns us to a world where particles have definite positions at all times. The randomness we observe in quantum experiments comes from our ignorance of initial conditions, not from some inherent indeterminism in nature. This might sound like a return to classical physics, but there's a crucial difference: non-locality. The pilot wave instantly influences particles across any distance, allowing for the spooky action at a distance that Einstein found so troubling. This non-locality is built into the theory, making it compatible with experimental results that violate Bell's inequality. Interestingly, we can visualize pilot waves in a macroscopic analog: oil droplets bouncing on a vibrating fluid surface. These droplets create waves that then guide the droplet's motion, creating patterns remarkably similar to quantum behavior, including double-slit interference. While this doesn't prove pilot wave theory, it provides a tangible model for understanding it. Despite its intuitive appeal, pilot wave theory hasn't gained widespread acceptance. Critics argue it adds complexity without new predictions, violating Occam's razor. It also struggles with relativistic extensions and quantum field theory, where the concept of particles with definite trajectories becomes problematic. Nevertheless, interest in pilot wave theory has grown in recent years. Some researchers believe it might offer new insights for quantum computing, while others see it as a stepping stone to deeper theories. The theory reminds us that the interpretation of quantum mechanics remains open. While the mathematics of quantum theory is well established, what it tells us about reality is still debated. Pilot wave theory offers a provocative alternative. Perhaps the quantum world isn't inherently random or observer-dependent. It's just guided by waves we can't directly observe. As you fall asleep, imagine tiny particles all around you, each following precise trajectories guided by invisible pilot waves, ripples in a cosmic ocean that connects all matter across space and time. Quantum Zeno effect. Imagine a watched pot that literally never boils because you're watching it. This strange scenario has a quantum parallel called the Quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, famous for his paradoxes about motion and change. This peculiar phenomenon reveals that repeatedly observing an unstable quantum system can actually prevent it from changing, as if freezing it in time through the act of measurement. Discovered experimentally in the 1970s, the quantum Zeno effect occurs when a quantum system is repeatedly measured at very short intervals. Normally, an unstable quantum state would decay or evolve into other states according to its natural probabilities. However, each measurement forces the system to reset to a definite state, effectively restarting the clock on its evolution. If these measurements happen frequently enough, the system becomes increasingly likely to remain in its initial state, as if frozen by observation. It's as if the quantum system never gets enough time between measurements to significantly change, always being forced back to square one. A classic demonstration involves excited atoms that would normally emit photons as they decay to lower energy states. When repeatedly measured to see if they're still excited, the atoms remain excited far longer than they would without measurement. The more frequent the measurements, the stronger the freezing effect. The effect is rooted in basic quantum mechanics. When a quantum system begins to evolve from one state to another, it doesn't switch instantly, but follows a probability curve. At very short times after starting in a particular state, the probability of finding it still in that state decreases quadratically, proportional to time squared, rather than linearly. This means that extremely brief evolutions are highly unlikely to show any change. Intriguingly, the quantum Zeno effect has a counterpart called the anti-Zeno effect, where frequent measurements can actually accelerate decay rather than inhibit it, depending on the system's properties and the type of measurement performed. Scientists have found practical applications for this effect. It can be used to protect fragile quantum states from decoherence in quantum computing, essentially using measurements to prevent errors from accumulating. It also has potential applications in precision spectroscopy and quantum control techniques. The effect raises profound questions about the nature of quantum measurement and time. It suggests that reality at the quantum level is vastly different from our intuitive understanding, where observation can literally halt natural processes. While the philosophical implications are fascinating, it's important to note that the quantum Zeno effect doesn't require consciousness or a human observer. Any interaction that effectively measures the quantum state will do, whether it's a detector or simply interactions with the environment. As you drift towards sleep, consider how strange it is that observation itself can influence physical processes at the quantum level, where simply looking at something can change how it behaves, as if reality itself responds to being watched. Quantum harmonic oscillator. The quantum harmonic oscillator might sound intimidatingly technical, but it's actually one of the most beautiful and important models in all of quantum mechanics. It describes a particle moving back and forth in a special type of potential, like a ball on a spring or a pendulum swinging. But when we apply quantum mechanics to this simple system, remarkable patterns emerge that help explain everything from molecular vibrations to the behavior of light. In classical physics, a harmonic oscillator is straightforward. A particle experiences a restoring force proportional to its displacement from equilibrium. Think of a weight on a spring. The further you pull it, the stronger it pulls back. The particle oscillates back and forth in a perfect sine wave, with its position and momentum changing continuously. When we apply quantum mechanics, everything changes. The particle can no longer have just any energy. Instead, its energy levels become quantized, existing only in discrete steps, like rungs on a ladder. Each energy level is separated by exactly the same amount, Planck's constant times the oscillator's frequency. This quantization leads to fascinating consequences. Even at its lowest energy state, called the ground state, the oscillator can never be completely at rest. The uncertainty principle forbids both position and momentum from being precisely zero simultaneously. This minimum energy, called zero-point energy, means quantum oscillators are always in motion, even at absolute zero temperature. The wave functions describing the oscillator's position probability form beautiful patterns called Hermit functions. The ground state looks like a bell curve centered at the equilibrium position. Higher energy states develop nodes, places where the particle can never be found. As the energy increases, these wave functions become increasingly complex, with more nodes and broader distribution. What makes the quantum harmonic oscillator so important is its ubiquity. It's an excellent approximation for many real-world systems: vibrating molecules, atoms in crystal lattices, electromagnetic fields, and even the fundamental particles in quantum field theory. When you listen to music, you're hearing quantum harmonic oscillators in action, the vibrating strings or air columns in instruments. Perhaps most remarkably, the electromagnetic field itself can be modeled as an infinite collection of quantum harmonic oscillators. The photons that make up light are nothing but excited states of these oscillators, quantized vibrations in the electromagnetic field. Even in quantum computing, harmonic oscillators play a crucial role. Some quantum computers use superconducting circuits that behave as artificial atoms with harmonic oscillator-like energy levels to store and process quantum information. The quantum harmonic oscillator exemplifies the beauty of theoretical physics, a simple model that reveals profound insights about how nature works at its most fundamental level. It shows how quantum mechanics imposes rhythm and pattern on the universe, allowing only certain vibrations and energies in the cosmic symphony. As you fall asleep, imagine the atoms in your bedroom as tiny quantum oscillators, gently vibrating according to the precise mathematics of quantum mechanics, each one dancing to nature's carefully quantized tune. Zero-point energy. At the very heart of quantum mechanics lies a profound and counterintuitive truth. There is no such thing as absolute stillness. Even at the lowest possible energy state, absolute zero temperature, where classical physics would predict complete motionlessness, quantum systems still harbor energy and fluctuate constantly. This residual energy is called zero-point energy, and it reveals that the universe never truly rests. The source of zero-point energy is Heisenberg's uncertainty principle, which states that complementary variables like position and momentum cannot both be precisely known simultaneously. For a particle to be completely motionless, it would need to have both a precise position to be at rest and a precise momentum, exactly zero. This is forbidden by quantum mechanics. As a result, quantum systems always retain some minimum energy, even at absolute zero. For a quantum harmonic oscillator, like a vibrating molecule, this zero-point energy equals 1/2 of Planck's constant times the oscillator's frequency. This means higher frequency systems have higher zero-point energies. Zero-point energy isn't just a theoretical curiosity. It has observable effect. In liquid helium, zero-point vibrations prevent the atoms from forming a solid, even at temperatures near absolute zero. This is why helium remains liquid unless extreme pressure is applied. Another manifestation is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum are drawn together. This happens because fewer vacuum fluctuations, manifestations of zero-point energy, can fit between the plates than outside them, creating a pressure difference. different. Zero-point energy also explains why atoms don't collapse. Classical physics suggests electrons should spiral into the nucleus, but the uncertainty principle prevents electrons from being precisely localized near the nucleus. Their zero-point energy keeps them in stable orbital state. In quantum field theory, all fields possess zero-point energy, creating a background vacuum energy permeating all of space. Theoretical calculations suggest this energy should be enormous, leading to what physicists call the vacuum catastrophe, or cosmological constant problem, as the observed cosmic vacuum energy is vastly smaller than predicted. This hasn't stopped speculation about harnessing zero-point energy as a potential power source. Unfortunately, despite claims from fringe science, extracting usable energy from the vacuum would violate established physical laws. Zero-point energy is the minimum energy state of a system. You can't go lower and extract that energy without violating fundamental principle. Nevertheless, understanding zero-point energy has practical applications in fields like chemistry, where it explains why certain chemical reactions proceed even at extremely low temperatures, and in designing quantum technologies that must account for these inescapable quantum fluctuations. As you drift towards sleep, consider that the atoms in your body are never truly still. Each one harbors zero-point energy, vibrating ceaselessly according to the fundamental laws of quantum mechanics, a perpetual, subtle dance that continues even as you rest. Quantum measurement problem. At the heart of quantum mechanics lies a profound mystery that has troubled physicists for nearly a century: the quantum measurement problem. It centers on a deceptively simple question: what happens when we measure a quantum system? This isn't just a technical detail. It's a fundamental puzzle about the nature of reality itself. In quantum mechanics, systems are described by wave functions that evolve smoothly and deterministically according to the Schrödinger equation. These wave functions represent probabilities for different possible states. A particle might exist in a superposition, simultaneously being in multiple positions or having multiple properties until measured. But something strange happens during measurement. The wave function appears to collapse suddenly from multiple possibilities to a single definite outcome. This collapse isn't described by the Schrödinger equation. It seems to be a completely different process. But what causes it? When exactly does it happen? And why does measurement have this special status? This abrupt transition from quantum probabilities to classical certainty is what physicists call the measurement problem. It reveals a fundamental inconsistency in quantum theory. We have one set of rules for how quantum systems evolve when not observed, and an entirely different set for what happens when we measure them. Numerous interpretations of quantum mechanics attempt to resolve this problem. The Copenhagen interpretation, the traditional view, simply accepts wave function collapse as a basic postulate of the theory without explaining its mechanism. Many worlds' interpretations suggest the wave function never collapses. Instead, all possible outcomes occur in different branches of reality, with observers in each branch seeing only one result. Other approaches include pilot wave theory, which maintains particles always have definite positions guided by a real physical wave. Objective collapse theories, where wave functions spontaneously collapse under certain conditions. And cubism, which treats quantum states as representing an observer's knowledge rather than objective reality. The measurement problem connects to deeper philosophical questions about consciousness and reality. Does consciousness cause wave function collapse, as some like Eugene Wigner initially suggested? Does objective reality exist independent of observation? Can a theory that makes perfect experimental predictions still be considered incomplete if it can't explain this fundamental process? Modern research has made progress through decoherence theory, which explains how quantum systems rapidly lose their quantum properties through interaction with their environment. While decoherence explains why we don't see quantum superpositions in everyday life, it doesn't fully resolve the measurement problem. It doesn't explain why one specific outcome occurs rather than another. As you contemplate sleep, consider this. The simple act of observation, of learning something about the world, might be far more profound than we ever imagined, perhaps even altering the fabric of reality in ways we still don't fully understand. The EPR paradox. In 1935, Albert Einstein and two colleagues, Boris Podolsky and Nathan Rosen, published a paper that presented one of the most famous challenges to quantum mechanics. Known as the EPR paradox, it exposed what Einstein called spooky action at a distance, a phenomenon that seemed to violate his deeply held belief that nothing could travel faster than light. The paradox centers on entangled particles, which have correlated properties. Imagine two particles created together, such that if one has an up spin, the other must have a down spin. According to quantum mechanics, neither particle has a definite spin until measured. They exist in a superposition of possibility. Yet when you measure one particle and find it's up, the other instantaneously becomes down, no matter how far apart they are. Einstein found this deeply troubling. How could the second particle know the result of a measurement on the first particle, especially if they're separated by vast distances? Such instantaneous influence seemed to contradict special relativity, which forbids faster-than-light communication. The EPR paper argued this presented quantum mechanics with a dilemma. Either quantum mechanics was incomplete, missing some hidden variable that predetermined the particle's properties, or it allowed for non-local effects where particles instantly influence each other across space, something Einstein considered impossible. Einstein believed in local realism, the idea that objects have definite properties independent of observation, realism, and that objects can only be influenced by their immediate surrounding, locality. The EPR paradox seemed to show that quantum mechanics violated at least one of these principles. For decades, the EPR paradox remained a philosophical puzzle rather than an experimental one. Then, in 1964, physicist John Bell devised a brilliant mathematical test. Bell showed that if hidden variables existed, as Einstein hoped, there would be strict limits on the correlations between entangled particles. These became known as Bell's inequalities. In the 1970s and 1980s, experiments by physicists, including Alain Aspect, measured these correlations in actual entangled particles. The results decisively violated Bell's inequalities, confirming quantum mechanics predictions and ruling out Einstein's hoped-for local hidden variables. The universe, it seemed, was non-local. Entangled particles really do influence each other instantaneously across any distance. Yet this doesn't actually violate special relativity because no useful information can be transmitted this way. The results of individual measurements remain random and unpredictable. The EPR paradox and its eventual resolution represent one of the great scientific dramas of the 20th century. Einstein's intuition about locality turned out to be wrong, but his skepticism pushed quantum theory to confront its deepest mysteries. The universe proved stranger than even Einstein imagined, a place where particles separated by light years maintain ghostly connections that transcend space itself. As you drift toward sleep, consider that the particles in your body may maintain subtle quantum connections with distant matter, linking you to the cosmos in ways that defy our everyday understanding of space and separation. Bell's theorem. In 1964, physicist John Bell published a paper that would revolutionize our understanding of quantum mechanics and reality itself. His theorem, often called the most profound discovery of science, provided a way to test whether the strange behaviors of quantum particles could be explained by hidden variables, unknown properties that might restore determinism and locality to physics, as Einstein had hoped. The story began with the EPR paradox, where Einstein, Podolsky, and Rosen highlighted how quantum mechanics seemed to allow entangled particles to influence each other instantaneously across any distance. Einstein considered this spooky action at a distance to be impossible, and suggested quantum mechanics must be incomplete, missing some hidden variables that would explain these correlations without faster-than-light influences. Bell approached this problem mathematically. He reasoned that if Einstein was right and hidden variables determined determined the properties of entangled particles from the moment of their creation, then the correlations between measurements on these particles would have to obey certain statistical limits. These became known as Bell's inequalities. Crucially, Bell showed that quantum mechanics predicts stronger correlations than would be possible with any local hidden variable theory. This meant the debate could be settled experimentally by measuring the correlations between entangled particles and checking whether they violated Bell's inequality. In the 1970s and 1980s, experiments led by physicists like Alain Aspect did exactly that. They created pairs of entangled photons, sent them in opposite directions, and measured their properties. The results consistently violated Bell's inequalities, confirming quantum mechanics and ruling out local hidden variables. These experiments proved something profound. No theory based on local hidden variables can reproduce all the predictions of quantum mechanics. Either locality, the principle that objects are only influenced by their immediate surrounding, or realism, the idea that particles have definite properties independent of observation, must be abandoned. Most physicists have concluded that locality is the principle that must go. The universe appears to be non-local at its core, with entangled particles maintaining instantaneous connections regardless of distance. Yet this non-locality can't be used to send faster-than-light signals, preserving the spirit of Einstein's relativity. Some physicists explore alternative explanations, like superdeterminism, where all events, including experimenters' choices, are predetermined, or retrocausality, where future events influence the past. But these approaches have their own profound implication for our understanding of reality. Bell's theorem isn't just a technical result in quantum physics, it's a watershed in human understanding. It shows that the universe is fundamentally different from our intuitive picture of it. Reality at its deepest level isn't made of separate objects with definite properties. It's a web of quantum connections where observation and reality are inextricably linked. As you relax into sleep tonight, remember that Bell's theorem revealed a universe more mysterious and interconnected than even Einstein imagined, where particles separated by galaxies remain connected in ways that transcend space itself. Quantum computing basics. Imagine trying to build a computer that doesn't just use ones and zeros, but can somehow use both at the same time. This isn't science fiction. It's quantum computing, and it works by harnessing some of the strangest properties of our universe. Normal computers, the kind you're probably using right now, work with bits. Each bit is either 0 or 1, like a light switch that's either off or on. But quantum computers use something called qubits, and this is where things get weird. A qubit can be 0, 1, or somehow both simultaneously, a state called superposition. Think about flipping a coin. While it's spinning in the air, is it heads or tails? Well, in a way, it's both until you catch it and look. Qubits are kind of like that, except they can actually perform calculations while in this both states at once condition. But there's more strangeness. Qubits can also be entangled with each other. When two qubits are entangled, whatever happens to one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he wasn't wrong about the spooky part. When I first studied quantum mechanics, I was confused by all these strange new concepts, said physicist Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. So what makes quantum computers special? They can solve certain problems much faster than regular computers. For example, factoring large numbers, something that would take a normal computer thousands of years, might take a quantum computer just seconds. This has huge implications for cryptography, the math that keeps your online banking secure. But don't throw away your laptop just yet. Quantum computers aren't replacing regular computers anytime soon. They're incredibly difficult to build and maintain. They need to be kept colder than outer space, about negative 273 degrees Celsius, to work properly, and they're still prone to errors. Companies like IBM, Google, and Microsoft are racing to build practical quantum computers. Google claimed quantum supremacy in 2019 when their quantum computer solved a problem that would have taken the world's fastest supercomputer thousands of years. We're still in the early days. Think of it as the 1950s of quantum computing, but the potential is mind-boggling. New medicines, better batteries, optimized shipping routes, improved artificial intelligence, and solutions to problems we haven't even thought of yet. Quantum bits and qubits. Let's dive into the nuts and bolts of quantum computing. The qubit. It's the fundamental unit of quantum information, and it's both simple and mind-bendingly complex. Classical computers use bits to store and process information. Each bit is either 0 or 1. It's like a coin showing either heads or tails. Easy, right? Now, throw that intuition out the window because qubits play by completely different rules. A qubit can exist as 0, 1, or a combination of both states at once, what physicists call a superposition. Imagine a coin spinning in the air. It's neither heads nor tails until you catch it and look. But in the quantum world, that spinning coin is actually doing useful work while it's in that undefined state. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical, said Richard Feynman, highlighting why we need quantum computers in the first place. How do we actually make a qubit? There are several ways: the spin of an electron, up, down, or both; the polarization of a photon, horizontal, vertical, or both; the energy level of an atom, ground state, excited, or both. IBM's quantum computers use superconducting circuits cooled to near absolute zero. Google uses similar technology. Microsoft is betting on topological qubits that are theoretically more stable. Each approach has its pros and cons. What makes qubits truly powerful is entanglement, when qubits become linked so that the state of one instantly affects the other, no matter the distance between them. Two entangled qubits can represent 4 states simultaneously: 0, 0, 0, 1, 1, 0, and 1, 1. 3 qubits can represent 8 states. With just 300 qubits, you could represent more states than there are atoms in the observable universe. But there's a catch. Qubits are incredibly fragile. The slightest interaction with their environment, a stray photon, a tiny fluctuation in temperature, can cause them to decohere and lose their quantum properties. It's like trying to balance a pencil on its tip. The smallest disturbance makes it fall over. That's why quantum computers need heavy shielding and extreme cooling. IBM's quantum computers operate at about minus 273 degrees Celsius, close to absolute zero, colder than outer space. Despite these challenges, scientists have made remarkable progress. From just a handful of qubits a decade ago, we now have machines with over 100 qubits. We're still far from the thousands or millions needed for some application, but the path forward looks promising, if winding. The uncertainty of time. Time might seem straightforward, the steady tick-tock of seconds marking our lives, but quantum physics turns this simple concept inside out. In the quantum world, time isn't just a backdrop against which events unfold. It's woven into the very fabric of reality in mind-bending ways. Werner Heisenberg's uncertainty principle is usually applied to position and momentum. The more precisely you know where something is, the less precisely you can know how fast it's moving. But a similar uncertainty applies to time and energy. The more precisely you measure the energy of a system, the less certain you can be about when the system has that energy. Time is what clocks measure, physicist Carlo Rovelli once said. But what exactly are clocks measuring? At the quantum level, this isn't just a philosophical question. It's a physical conundrum. Consider a simple atom absorbing or emitting light. Classical physics would say this happens at a specific moment, but quantum physics shows that if the energy transfer is very precise, the exact moment it happens becomes fuzzy and uncertain. For very short time intervals, energy can even be borrowed from the vacuum. Particles can pop in and out of existence as long as they disappear quickly enough. This time-energy uncertainty has practical effects. It's why atoms have a natural line width in their emission spectra. It's why excited states have finite lifetime. The universe literally prohibits perfect precision in both time and energy measurements simultaneously. Time in the quantum realm gets even weirder. In Richard Feynman's path integral formulation, particles don't just travel along a single path through space and time. They simultaneously take all possible paths, each with its own probability amplitude. It's as if time itself branches and reconnects at every moment. In quantum theory experiments, we've seen that the order of events can even become ambiguous. In quantum switch experiments, physicists have demonstrated that it's possible to create situations where it's impossible to tell which of two events happened first. Both orderings exist in superposition. There's also the delayed choice quantum eraser experiment, where a choice made now appears to affect what happened in the past. It's not actually changing the past. Quantum mechanics preserves causality, but it sure looks that way from our classical perspective. Some physicists, like Julian Barber, have even suggested that time might not be fundamental at all, but emerges from quantum entanglement between systems. In this view, the flow of time is an illusion created by our macroscopic perspective. The quantum eraser. The quantum eraser experiment might be one of the weirdest demonstrations of quantum mechanics ever devised. It's like a magic trick that seems to reach backward in time, erasing and restoring information in ways that challenge our basic understanding of reality. At its heart, the experiment is an extension of the famous double-slit experiment. When you send particles, like photons, through two slits, they create an interference pattern on a screen behind them, acting like waves that overlap. But if you try to observe which slit each photon goes through, the interference pattern vanishes, and the photons act like particles. This is weird enough already. It's as if the photons know they're being watched and change their behavior. But the quantum eraser takes this strangeness to a whole new level. I think I can safely say that nobody understands quantum mechanics. Richard Feynman once remarked, "The quantum eraser might be the clearest justification for this statement." Here's how it works. Scientists set up a version of the double-slit experiment, but add a way to mark which slit each photon passes through using polarization. Think of it as giving each photon a name tag. As expected, this destroys the interference pattern. But here's the mind-bending part. They then add another device that can erase this which path information after the photon has already passed through the slits, but before it hits the final screen. When this erasure happens, the interference pattern mysteriously reappears. It's as if the photon's past behavior is changed by what you choose to do after it's already made its journey. Some interpretations make it seem like information is traveling backward in time, though physicists are quick to point out that no actual causality violation occurs. The delayed choice experiments are a very clever way of catching nature with its pants down, as physicist John Wheeler put it. In more sophisticated versions like the delayed choice quantum eraser, the setup is even more bizarre. Scientists use entangled photon pairs, where observing one photon can instantly affect its partner, no matter the distance between them. One photon goes through the slits, while its partner is sent in a different direction. By measuring the partner photon in certain ways, experimenters can retroactively determine whether its twin displayed wave-like or particle-like behavior. What makes this truly strange is that you can choose whether to erase the which path information long after the first photon has been detected. It's as if you're reaching into the past to change what has already happened. Quantum phase. When you think of a wave like ripples on a pond or a sound wave traveling through air, you might picture peaks and troughs moving along. In physics, we track a wave's phase to identify where in its cycle it is, at its peak, trough, or somewhere in between. In the quantum world, phase becomes something far stranger and more powerful. Quantum phase isn't just a property of wave, but a fundamental aspect of quantum systems that can lead to some of the most bizarre and useful phenomena in physics. Unlike classical waves you can see or feel, quantum phase exists in the complex mathematical space that describes quantum particles. The famous double-slit experiment provides a perfect illustration of quantum phase in action. When a particle passes through two slits, its quantum wave function splits and then recombines. Where the peaks meet peaks, we get constructive interference. Bright spot. Where peaks meet troughs, we get destructive interference. Dark spot. This interference pattern depends entirely on the relative phases of the waves. The phase is the most important concept in quantum mechanics, said physicist Richard Feynman, yet it is completely invisible to direct measurement. Indeed, you can never directly measure the absolute phase of a quantum system. Only relative phase differences matter, yet these invisible phase relationships control everything from chemical reactions to superconductivity. Quantum phase becomes particularly important in quantum computing. Much of a quantum computer's power comes from its ability to manipulate the phases of qubits. In fact, many quantum logic gates are essentially sophisticated phase shifters, changing the relative phases between different parts of the quantum system to perform calculation. One of the most dramatic demonstrations of quantum phase is the Aharonov-Bohm effect, where a charged particle can be affected by electromagnetic fields, even in regions where the particle never traveled. The particle's phase is altered by the presence of a magnetic field enclosed in a path the particle circles around but never enters. It's like feeling the gravity of a planet you've never visited. Perhaps most fascinating is the concept of geometric phase, or Berry phase, where a quantum system that undergoes a cycle of changes can accumulate a phase shift that depends only on the path taken through parameter space, not on how quickly the path is traversed. This geometric phase is behind phenomena like the quantum Hall effect and plays a crucial role in certain approaches to quantum computing. Quantum phase also appears in macroscopic quantum phenomena like superfluidity and superconductivity, where large collections of particles share a common phase, creating effects visible to the naked eye. Quantum numbers. Imagine trying to describe every person on Earth. You'd need multiple characteristics: height, weight, age, location, to distinguish one from another. Quantum particles have their own set of identifying characteristics called quantum numbers. These aren't just labels, they're the foundation of how matter behaves at its most fundamental level. The quantum numbers are like an ID card for particles, telling us everything we need to know about them. They emerge naturally from solving the Schrödinger equation, the master equation of quantum mechanics, and are essential to understanding atomic structure, chemical bonding, and even why the periodic table is arranged the way it is. Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry, said Richard Feynman, highlighting how these abstract numbers create the ordered reality we experience. The four primary quantum numbers for electrons are the principal quantum number, n. This determines the electron's energy level and how far it is from the nucleus on average. It can be any positive integer, 1, 2, 3. Higher values mean higher energy and greater distance from the nucleus. The angular momentum quantum number, L. This describes the shape of the electron's orbital. It can be any integer from 0 to n-1. Each value corresponds to a different orbital shape. L equals 0 is an s orbital, spherical. L equals 1 is a p orbital, dumbbell shape, and so on. The magnetic quantum number ml. This specifies the orientation of the orbital in space. It can be any integer from negative L to positive L, giving a total of 2L plus 1 possible orientations. The spin quantum number, ms. This represents the electron's intrinsic angular momentum, or spin. It can only be plus 1/2 or minus 1/2, often called spin up or spin down. The profound insight of quantum mechanics is that these numbers can't take just any value. They're quantized, meaning they can only take specific discrete values. This quantization leads directly to the stability of atoms and the entire structure of matter. When atoms bond to form molecules, it's the interplay of electrons with different quantum numbers that determines the shape and properties of the resulting compound. The entire field of chemistry is built upon this quantum foundation. Quantum numbers also obey various rules, like the Pauli exclusion principle, which states that no two electrons in an atom can have the same set of quantum numbers. This principle explains why electrons fill different energy levels rather than all crowding into the lowest state, giving rise to the rich structure of the periodic table. The Pauli exclusion principle. Imagine trying to sit in a chair that's already occupied. You can't. Two objects can't occupy the same space at the same time. That's common sense. But at the quantum level, particles follow a similar rule for much stranger reasons. This is the Pauli exclusion principle, and without it, the universe as we know it wouldn't exist. Named after Austrian physicist Wolfgang Pauli, who formulated it in 1925, the principle states that no two identical fermions, particles with half-integer spin like electrons, protons, and neutrons, can occupy the same quantum state simultaneously. In simpler terms, electrons in an atom can't have the exact same set of quantum numbers. They need to differ in at least one respect. God made the bulk. Surfaces were invented by the devil, Pauli once quipped, hinting at the complexities that emerge from this seemingly simple rule. This principle isn't just some abstract law. It's why matter has structure and takes up space. Without it, all electrons would collapse into the lowest energy level of atom, making chemistry impossible. There would be no different elements, no chemical reactions, no you or me. The exclusion principle explains why electrons arrange themselves in shells around atomic nuclei. The first shell can hold 2 electrons, one spin up, one spin down. The second shell can hold 8 electrons, and so on. This arrangement gives atoms their size and chemical properties, creating the diversity of elements in the periodic table. It's also responsible for everyday phenomena. When you sit on a chair, you're not actually touching it. The electrons in your body are repelling the electrons in the chair due to the Pauli exclusion principle. Your entire sensory experience of the physical world is largely the result of this quantum effect. In white dwarf stars, which have exhausted their nuclear fuel, it's electron degeneracy pressure from the Pauli exclusion principle that prevents gravitational collapse. Similarly, in neutron stars, neutron degeneracy pressure holds against gravity. Without these quantum effects, these stars would immediately collapse into black holes. The principle also plays a crucial role in superconductivity, where electrons form Cooper pairs that can behave like boson particles not subject to the exclusion principle, allowing them to condense into a state with zero electrical resistance. Remarkably, the Pauli exclusion principle emerges from relativistic quantum field theory and is connected to the spin statistics theorem. It's not an ad hoc rule, but a deep consequence of the symmetry requirements of quantum mechanics, combined with special relativity. From the structure of atoms to the properties of neutron stars, from the hardness of matter to the chemistry of life, the Pauli exclusion principle shapes our universe in profound and fundamental ways. Quantum spin. Spin is one of the quantum world's most misleading terms. When physicists first discovered that electrons had an intrinsic angular momentum, they imagined these tiny particles actually spinning like tops. We now know that's not the case. Quantum spin is a purely quantum property with no classical counterpart, yet it shapes our universe in profound ways. Unlike a spinning ball, quantum spin is quantized. It comes in fixed units and can't take just any value. Electrons, protons, and neutrons have a spin of 1/2, meaning they must rotate 720 degrees, not 360, to return to their original state. This bizarre property makes them fermion, particles that obey the Pauli exclusion principle. If I could remember the names of all these particles, I'd be a botanist, joked Enrico Fermi. Indeed, classifying particles by their spin is fundamental to understanding their behavior. Particles with integer spin 0, 1, 2 are called bosons. These include photon, light particles, and the recently discovered Higgs boson. Bosons don't mind sharing. They can occupy occupy the same quantum state simultaneously. This property enables lasers, where photons pile into identical states to create coherent light, and Bose-Einstein condensates, where atoms cool so much they behave as a single quantum entity. Spin determines how particles interact with magnetic fields. This is the principle behind MRI machines. By aligning the spins of hydrogen nuclei in your body and then detecting how they relax back to their natural state, doctors can create detailed images of your internal organs without harmful radiation. But spin strangeness goes deeper. It follows different mathematics than classical rotation. Specifically, it uses the mathematics of something called SU2 symmetry rather than the SO3 symmetry of ordinary rotation. This means spin states transform in ways that would be impossible for classical objects. This peculiarity leads to fascinating quantum effects. In quantum computing, electron spins can serve as qubits, quantum bits that can be 0, 1, or both simultaneously. Such spin qubits are among the most promising approaches for building practical quantum computers. Spin also plays a crucial role in spintronics, an emerging field that exploits electron spin rather than charge for computing. Your computer's hard drive already uses giant magnetoresistance, a spin-based effect that earned the 2007 Nobel Prize in Physics. God used beautiful mathematics in creating the world, said Paul Dirac, who developed the relativistic equation describing electron spin. Indeed, the mathematics of spin reveals deep connections between quantum mechanics and geometry, showing how the most abstract mathematics can describe fundamental aspects of physical reality. Path integral formulation. Imagine you want to get from your house to a friend's place across town. Common sense says you'd take the most direct route. But what if instead you took every possible path simultaneously, zigzagging through side streets, looping around parks, even briefly heading in the wrong direction, and somehow these infinite possibilities combined to determine your actual journey? This bizarre scenario captures the essence of Richard Feynman's path integral formulation of quantum mechanics. Traditional quantum mechanics describes particles using wave functions that evolve according to the Schrödinger equation. Feynman's approach, developed in the 1940s, offered a radical alternative. To find the probability of a particle going from point A to point B, you must consider every possible path it could take between those points, assign each path a complex number called an action, and then sum over all paths. Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry, Feynman wrote, hinting at how individual paths contribute to the whole. In classical physics, a particle follows the path of least action, like a ball rolling along the shortest route. But in quantum mechanics, a particle takes all paths simultaneously. Each path contributes a phase factor, essentially a complex number on the unit circle, determined by the action along that path. When you add these phases together, most paths cancel out through destructive interference, while paths near the classical path constructively interfere, making them more probable. This explains why quantum objects sometimes behave like particles and sometimes like waves. The path integral naturally incorporates interference effect, as the phases from different paths combine like waves overlapping. The mathematics gets complicated quickly. Even for simple systems, you're integrating over an infinite dimensional space of possible paths. Yet this formulation has proven remarkably powerful, especially in quantum field theory, where it's the standard approach for calculating particle interaction. Path integrals also reveal deep connections between quantum mechanics and statistical mechanics. By making time imaginary, a mathematical trick involving the complex number I, the quantum path integral becomes equivalent to a statistical average over configurations in thermal equilibrium. This formulation has inspired applications beyond physics. In finance, path integrals help price options by considering all possible future price trajectories. In computer science, they've influenced algorithms for global optimization problems. Perhaps most profoundly, the path integral formulation suggests a different way of thinking about reality itself. Rather than particles following definite trajectories, the quantum world is a blur of all possibilities, weighted by probability. The sharp, definite world we perceive emerges only statistically from this quantum fuzziness. Quantum coherence. Quantum coherence is like a perfect orchestra where every instrument plays in exact synchronization. Except instead of violins and cellos, we're talking about quantum waves maintaining perfect relationships with each other. This delicate harmony lies at the heart of quantum computing, superconductivity, and possibly even certain biological processes. In classical physics, objects exist in definite states. A coin is either heads or tails, but quantum systems can exist in superposition, simultaneously in multiple states with specific phase relationships between them. This is quantum coherence, the perfect preservation of these phase relationships across the different components of a quantum state. I think I can safely say that nobody understands quantum mechanics, Richard Feynman famously remarked. Coherence is a prime example of why it enables behaviors that seem impossible from our everyday experience. Consider a qubit in a superposition of 0 and 1. As long as it maintains coherence, both states coexist in a precise mathematical relationship. This allows quantum computers to explore multiple solutions simultaneously, giving them their potential power. But coherence is incredibly fragile. Anything that interacts with a coherent quantum system, stray photon, thermal vibration, electromagnetic field, can disrupt these delicate phase relationships, causing decoherence. This is why quantum computers need extreme isolation and cooling to operate. Decoherence is like trying to build a sandcastle with dry sand, explains physicist Wojciech Zurek. The moment you try to stack it, it falls apart. This process explains why we don't see quantum behavior in everyday objects. Even a dust particle is constantly interacting with air molecules, photons, and gravitational fields, causing any quantum coherence to decay almost instantly, a process called environmental decoherence. But some systems can maintain coherence longer than others. Superconductivity works because electrons form Cooper pairs that move coherently through a material without energy loss. Lasers produce coherent light, where all photons have synchronized phases, and recent evidence suggests that certain biological processes like photosynthesis and bird migration might exploit quantum coherence to achieve remarkable efficiency. Scientists are developing various techniques to protect quantum coherence, like quantum error correction codes, topological protection, and dynamical decoupling. These approaches are crucial for practical quantum computing and other quantum technologies. Quantum coherence also highlights fundamental questions about the nature of reality. The famous Schrödinger's cat thought experiment illustrates the puzzle. If quantum systems can exist in coherent superpositions, why don't we see cats that are simultaneously alive and dead? The various interpretations of quantum mechanics, from Copenhagen to many worlds to quantum decoherence, all attempt to resolve this apparent paradox. Whether it's enabling quantum computing, explaining material properties, or challenging our understanding of reality itself, quantum coherence remains one of the most fascinating and useful aspects of quantum theory. The Aharonov-Bohm effect. Imagine standing outside a tall, sealed building. You can't go inside and there's no way to see what's in there. Suddenly, you notice your compass needle is deflected, even though you can't detect any magnetic field where you're standing. Something inside that building is affecting your compass from a distance without any apparent direct interaction. This is essentially the Aharonov-Bohm effect, a phenomenon where particles are influenced by electromagnetic fields that exist in regions the particles never enter. Discovered theoretically in 1959 by Yakir Aharonov and David Bohm, and confirmed experimentally in the 1960s, this effect revealed something profound. In quantum mechanics, electromagnetic potentials, not just fields, can have physical significance. In classical physics, only fields affect particles, but Aharonov and Bohm showed that in quantum mechanics, potentials matter even where fields vanish, explained physicist Richard Feynman when discussing this revolutionary idea. The classic experiment involves a magnet enclosed within a shielded region, creating a magnetic field that's completely contained inside. Electrons are then sent in two possible paths around this region, but never through it, and allowed to interfere. Astonishingly, even though the electrons never experience any magnetic field. Their interference pattern shifts depending on the strength of the enclosed magnetic field. This seems magical, like the electrons somehow know about the magnetic field they never encounter. But the explanation lies in the quantum mechanical phase, the electromagnetic potential, called the vector potential, which extends beyond the region containing the magnetic field, shifts the phase of the electron's wave function. When the two paths recombine, this phase shift affects the interference pattern. The Aharonov-Bohm effect has deep implications. It demonstrates that in quantum mechanics, potentials are more fundamental than fields. It shows that the electromagnetic potential is not just a mathematical convenience, as in classical physics, but has real, measurable effects. And it highlights the non-local nature of quantum mechanics. Particles can be affected by conditions in regions they never visit. This effect has practical applications too. It forms the basis for many quantum interference devices, including superconducting quantum interference devices, SQUIDs, used in extremely sensitive magnetometers. These can detect magnetic fields so weak they can measure the magnetic fields produced by brain activity. The Aharonov-Bohm effect also generalizes to other gauge fields in physics. Similar effects occur in condensed matter systems, where they reveal properties of exotic quantum states of matter. Perhaps most profoundly, this effect demonstrates that in quantum mechanics, the global properties of a system can affect local behavior. The quantum world is interconnected in ways that have no classical analog, challenging our intuitive understanding of reality. Quantum teleportation. Beam me up, Scotty. While Star Trek's transporters remain firmly in the realm of science fiction, quantum teleportation is very real, though not quite what most people imagine. It doesn't involve zapping physical objects across space, but rather transferring the exact quantum state of one particle to another, potentially far away, without physically moving the original particle. First demonstrated experimentally in 1997, quantum teleportation relies on one of quantum mechanics' strangest features, entanglement. When two particles are entangled, their properties become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. Spooky action at a distance, Einstein called it. Never quite comfortable with the concept. But this spookiness is precisely what makes quantum teleportation possible. Here's how it works. Alice and Bob share an entangled pair of particles. Alice has another particle whose quantum state she wants to teleport to Bob. She performs a special joint measurement on her entangled particle and the particle to be teleported. This measurement doesn't reveal the state being teleported, preserving quantum no-cloning rules, but it does place Bob's particle in a state related to the original. Alice then sends Bob the results of her measurement through a classical channel, like a phone call. Based on this information, Bob performs specific operations on his particle, transforming it into an exact replica of the original state Alice wanted to teleport. The original state is destroyed in the process. It's teleportation, not copying. It's not like the original particle disappears from where it is and reappears somewhere else, explains physicist Anton Zeilinger, a pioneer in quantum teleportation. What we're sending is the information about the particle's state, not the particle itself. The applications are profound. Quantum teleportation is a key mechanism for quantum networks and the future quantum internet. It allows quantum states to be transferred between quantum computers or other quantum devices without losing their delicate quantum properties. It's also essential for quantum repeaters, which would extend the range of quantum communication. Scientists have steadily improved quantum teleportation capability. Initially demonstrated with photons over a few meters, it has since been achieved over distances exceeding 100 kilometers through both fiber optics and free space. Researchers have teleported multiple properties simultaneously and worked with various types of quantum systems. While we won't be teleporting humans or even microscopic objects anytime soon, if ever, quantum teleportation represents a fundamental capability for quantum technology. It demonstrates the profound interconnectedness of quantum systems and provides a mechanism for transferring quantum information, a crucial requirement for the quantum networks of the future. Quantum cryptography. In the high-stakes world of encryption, quantum cryptography represents something remarkable, a method of secure communication that's theoretically unbreakable, not because of computational difficulty, but because of the fundamental laws of physics themselves. Traditional encryption methods rely on mathematical problems that are hard to solve without the right key. But hard doesn't mean impossible, just impractical with current computing power. Quantum computers threaten to break many of these systems, creating an urgent need for alternatives. Enter quantum cryptography, specifically a technique called quantum key distribution, QKD. Unlike conventional methods, QKD uses the principles of quantum mechanics to establish secure communication channels. Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, said Richard Feynman. The same applies to truly secure communication. The most widely implemented QKD protocol, BB84, named after its inventors Charles Bennett and Gilles Brassard, and the year 1984, works by encoding information in the quantum states of particles, typically photons. Here's the elegant part. According to quantum mechanics, measuring a quantum system disturbs it. So if an eavesdropper tries to intercept the quantum transmission, they'll inevitably alter the quantum states in a detectable way. It's like a letter that changes its contents if someone opens the envelope along the way. When sending quantum encoded keys, Alice and Bob can detect any eavesdropping attempt by comparing a small portion of their keys. If too many discrepancies exist, they know someone was listening and abandon that key. If the key checks out, they can use it to encrypt their actual message using conventional methods. QKD has moved beyond theory to commercial systems now operating in various parts of the world. In 2017, China launched the world's first quantum communication satellite, Mikius, establishing quantum encrypted links across thousands of kilometers. Banks, government agencies, and other security-conscious organizations are increasingly adopting this technology. But quantum cryptography isn't without challenges. Current implementations have distance limitations due to photon loss in optical fibers. There's also the problem of side-channel attacks, targeting not the quantum protocol itself, but the physical implementation. Perhaps most significantly, QKD only solves the key distribution problem, not all aspects of secure communication. You still need secure authentication method to ensure you're really talking to the intended recipient. Despite these limitations, quantum cryptography represents a fascinating case where the weirdness of quantum mechanics provides practical benefit. As physicist Bennett put it, it's as if the quantum world is saying, you can look but don't touch, and we've turned that into a security advantage. Quantum entanglement applications. The spooky connections of quantum entanglement aren't just philosophical curiosities. They're becoming the foundation of revolutionary technologies that could transform our world. From unhackable communications to medical breakthroughs, entanglement is escaping the physics lab and entering our everyday lives. Quantum communication networks may be the first widespread application. Traditional encryption will eventually fall to powerful quantum computers, but entanglement offers a solution. Quantum key distribution uses entangled particles to create encryption keys that change if anyone eavesdrops. China's Mikius satellite has already demonstrated entanglement-based communication across thousands of kilometers, laying groundwork for a future quantum internet with unprecedented security. Quantum networks will change not just how we communicate, but what we can communicate. They enable tasks that are simply impossible with classical networks. Beyond communication, quantum sensors leverage entanglement for extraordinary precision. Entangled particles can overcome the standard quantum limit, a boundary that typically restricts measurement precision. This enables gravity sensors that can detect underground structures, magnetic sensors that monitor brain activity with unprecedented detail, and clocks so precise they can measure relativistic time dilation at the scale of everyday human height. In medicine, entanglement-enhanced MRI machines could detect molecular changes related to diseases long before symptoms appear. Researchers at the University of Stuttgart have demonstrated that entangled light particles can improve imaging quality while reducing the radiation exposure for patients. Perhaps the most transformative application is quantum computing. When qubits become entangled, their computational power grows exponentially rather than linearly. A quantum computer with just 300 fully entangled qubits could, in principle, represent more states simultaneously than there are atoms in the observable universe. Entanglement is a resource. Just as we learn to use electricity or nuclear energy, we're learning to harness entanglement to do things otherwise impossible. Emerging fields like quantum machine learning are exploring how entanglement might lead to artificial intelligence capabilities far beyond current approaches. Meanwhile, quantum simulators use controlled entanglement to model complex quantum systems like high-temperature superconductors or photosynthesis, potentially leading to room temperature superconductivity or more efficient solar cells. There are even proposals for quantum batteries that use entanglement to achieve faster charging and higher energy densities than conventional batteries. As you drift towards sleep, imagine future technologies woven from entanglement, quantum GPS systems that work underwater, financial networks secured by the laws of physics, and medical diagnostics that can detect individual cancer cells. The quantum future isn't just coming. In some ways, it's already here, built on the strange connectedness that Einstein found so disturbing. Quantum biology. For decades, biologists and physicists lived in separate worlds. Conventional wisdom held that the delicate, weird effects of quantum mechanics couldn't possibly survive in the warm, wet, chaotic environment of living cells. That consensus has shattered over the past 20 years, giving rise to quantum biology, a field exploring how life might harness quantum effects, not just occasionally, but as essential operating principles. The first solid evidence came from an unexpected place: bird navigation. European robins and other migratory birds can sense Earth's magnetic field for navigation. But how? Research suggests a quantum mechanism called radical pair formation. When light hits special proteins in birds' eyes, it creates entangled electron pairs, whose quantum states are sensitive to magnetic field. This quantum compass helps birds see magnetic field lines, enabling their remarkable navigational feats. It's astonishing. Birds are essentially performing quantum measurements with their eyes. Even more fundamental is photosynthesis, the process that powers almost all life on Earth. When plants capture sunlight, the resulting energy must navigate a complex network of molecules to reach reaction centers. Rather than taking a single path, this energy appears to explore multiple routes simultaneously as a quantum coherent wave, finding the most efficient path with extraordinary speed. This quantum exploration helps plants achieve near-perfect energy transfer efficiency. Perhaps most surprising is the quantum nature of our sense of smell. The conventional lock and key model, where molecules fit receptors like physical keys, fails to explain how we distinguish between molecules with identical shapes but different vibrations. Quantum biology suggests electron tunneling, a purely quantum effect where particles pass through energy barriers, helps detect these vibrational frequencies, explaining our remarkable olfactory sensitivity. There's even emerging evidence that quantum effects might play roles in enzyme catalysis, where tunneling helps hydrogen atoms efficiently move between molecules, and potentially in DNA mutation, where quantum effects could influence how genetic changes occur. Critics initially argued that quantum coherence couldn't survive the body's warm environment, but research shows certain biological structures may actually protect quantum effects. Some proteins appear to shield quantum processes from disruption, allowing them to persist hundreds of times longer than they would in non-biological settings. Life may have evolved to the quantum edge, operating in a zone where quantum effects enhance biological function. As this young strong field develops, it raises profound questions. Did life evolve to exploit quantum mechanics, or was quantum mechanics essential for life to emerge at all? The boundary between the quantum and living worlds isn't just blurry, it might not exist at all. As you rest, consider that your body might be performing countless quantum calculations right now, from neural processes to enzyme activities, all in the seemingly classical world of living systems. The quantum brain. Is your conscious experience, your thoughts, perceptions, and sense of self fundamentally quantum mechanical? This provocative question has divided neuroscientists and physicists for decades, giving rise to both groundbreaking research and controversial speculation about quantum effects in the brain. The conventional view holds that neurons operate classically. Electrochemical signals travel through networks, creating the emergent phenomenon we call consciousness. On this view, the brain is essentially a complex classical computer, albeit one with remarkable capabilities. Quantum effects, though present at the atomic level, are thought to be irrelevant to neural function. The brain is too warm, wet, and massive for quantum effects to matter, argue many physicists, who calculate that quantum coherence in neurons would decay far too quickly, within a tiny fraction of a second, to influence cognition. Yet a minority perspective, championed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, proposes that consciousness emerges from quantum computations in cellular structures called microtubules. Their orchestrated objective reduction theory suggests these protein lattices could sustain quantum coherence long enough to influence neural activity, potentially explaining consciousness as a fundamental quantum process. While controversial, recent findings have offered some support. Research shows quantum coherence can survive in warm biological systems, like photosynthetic complexes, far longer than previously thought. Meanwhile, experiments suggest certain anesthetics work by disrupting quantum processes in microtubules rather than cellular membranes, potentially linking quantum effects to consciousness. Beyond microtubules, other researchers explore quantum effects in phenomena like the binding problem, how the brain creates unified perceptions from distributed processing. Quantum entanglement provides a theoretical framework for how separate neural processes might be integrated instantaneously. Even conventional neuroscience models increasingly recognize quantum influences. Neurotransmitter release involves electron tunneling, while the conformational states of proteins essential to neural function are governed by quantum probability distribution. Perhaps most intriguing is how quantum biology might inform the hard problem of consciousness, why subjective experience exists at all. Physicist David Bohm proposed that consciousness might emerge from a deeper quantum order beneath classical reality, while others suggest quantum measurement itself might be linked to consciousness. Quantum mechanics makes perfectly clear that observations performed by different observers are different. That's not a complicated notion at all. That's why quantum mechanics forces us to think about consciousness. Whether quantum mechanics merely provides the subatomic background for classical brain function or plays an active, essential role in consciousness remains an open question. But the quest reveals fascinating possibilities at the intersection of physics and neuroscience. As you close your eyes tonight, consider that the boundary between your conscious mind and the quantum realm may be thinner than we once imagined. Schrödinger's equation. At the heart of quantum mechanics lies one of physics' most elegant and powerful mathematical expressions, the Schrödinger equation, developed by Austrian physicist Erwin Schrödinger in 1925. This unassuming formula describes how quantum systems evolve over time, effectively serving as the master equation for much of quantum physics. The time-dependent Schrödinger equation looks deceptively simple when written mathematically. In this compact form lies the machinery that governs the behavior of electrons, atoms, and molecules, the foundation of our physical world. Unlike classical equations of motion, where particles have definite trajectories, Schrödinger's equation deals with probability waves. The wave function doesn't directly represent anything physical. Rather, its square gives the probability of finding a particle in a particular state. As this wave function evolves according to the equation, the probabilities change, creating the dynamic quantum dance we observe in experiments. The task is not to see what has never been seen before, but to think what has never been thought about what you see every day, Schrödinger once said. His equation exemplifies this philosophy, offering a radically new way to understand familiar phenomena. What makes the equation so powerful is its universality. Whether describing a single electron, a complex molecule, or even theoretically an entire universe, the basic structure remains the same. Only the total energy operator, which represents the total energy of the system, changes to reflect different situations. When Schrödinger first published his equation, he demonstrated its power by deriving the energy levels of hydrogen atoms, results that perfectly matched experimental observation. This success was astonishing, as previous models had struggled to explain atomic behavior. The Schrödinger equation also provided insight into chemical bonding, tunneling, and countless other quantum phenomena. It forms the basis for computational chemistry, allowing scientists to model molecular interactions with remarkable accuracy. Everything from drug design to material science relies on solving Schrödinger's equation for increasingly complex systems. There's a profound beauty in how the equation combines time, energy, and probability. The presence of the imaginary number, the square root of -1, connects time evolution to the wave-like nature of quantum systems, while Planck's constant bridges the quantum and classical world. Despite its success, Schrödinger's equation has limitations. It's not compatible with special relativity, leading to the development of relativistic quantum mechanics and eventually quantum field theory. And the equation itself gives no insight into the measurement problem. What happens when wave functions suddenly collapse upon observation? But even with these limitations, the Schrödinger equation stands as one of science's greatest achievements, a mathematical window into the quantum realm that continues to yield insights nearly a century after its discovery. As you drift towards sleep, imagine the wave functions of countless particles evolving according to this elegant equation, creating the quantum tapestry that underlies our reality. The quantum tunneling microscope. In 1981, two IBM researchers, Gert Binnig and Heinrich Rohrer, leveraged one of quantum mechanics' strangest phenomena to create a revolutionary device, the scanning tunneling microscope. This remarkable invention not only allowed scientists to see individual atoms for the first time, but also exemplified how quantum weirdness could be harnessed for practical applications. The microscope works by exploiting quantum tunneling, the ability of particles to pass through energy barriers they shouldn't be able to cross, according to classical physics. When an extremely sharp metal tip is brought incredibly close to a surface, just a few atoms away, electrons can tunnel across the gap between them, creating a measurable electric current. It was as if we had gained new eyes, Binnig said after their discovery, which earned them the 1986 Nobel Prize in Physics. What makes this microscope extraordinary is its precision. By measuring how the tunneling current varies as the tip scans across a surface, the microscope creates detailed topographical maps showing individual atoms and bonds between them. The tunneling current is exponentially sensitive to distance. If the gap increases by just 1/10 of a nanometer, about the diameter of an atom, the current typically decreases by a factor of 10. This sensitivity allows for resolution far beyond what was previously possible. Traditional optical microscopes are limited by the wavelength of light to resolutions of about 200 nanometers. The tunneling microscope smashed this limit, achieving resolutions measured in picometers, more than 1,000 times smaller. Beyond just seeing atoms, the microscope opened the door to manipulating them directly. In 1989, IBM researchers famously arranged 35 xenon atoms to spell out the company's logo, creating one of the first human-made structures, built atom by atom. This demonstration launched the field of nanotechnology, where materials are engineered at the atomic scale. Tunneling microscopes have revolutionized surface science, materials research, and semiconductor development. They've revealed the atomic structure of high-temperature superconductors, monitored chemical reactions at the atomic level, and helped develop ever smaller electronic components. The invention also spawned a family of related tools called scanning probe microscopes, including atomic force microscopes that can image non-conductive samples and even individual molecules in biological systems. Perhaps most profoundly, the tunneling microscope transformed quantum tunneling from a theoretical curiosity into a practical tool. What had been seen as a strange, almost philosophical aspect of quantum mechanics became the basis for a technology that has fundamentally changed our understanding of the material world. In science, the best verifications come when you translate theory into tools. The tunneling microscope turned quantum tunneling into one of humanity's most powerful ways of seeing the invisible. As you close your eyes tonight, consider how the strangest aspects of quantum physics, effects that seem to defy common sense, can become the foundation for technologies that extend human perception beyond what anyone thought possible. Quantum dots. Imagine particles so small they're sometimes called artificial atoms, nanoscale semiconductor crystals with unique properties that bridge the classical and quantum world. These are quantum dots, and they're transforming technologies from television displays to medical imaging and potentially quantum computing. Quantum dots are tiny semiconductor particles, typically between 2 and 10 nanometers in diameter, so small that the electrons inside them are confined in all three spatial dimensions. This confinement creates quantum effects that wouldn't appear in larger materials, effectively turning quantum dots into customizable quantum systems. When you confine electrons to nanoscale semiconductor structures, their properties change dramatically. The most obvious change is in color. Quantum dots of the same material emit different colors depending solely on their size. This size-dependent color results from quantum confinement. As the dot gets smaller, the energy levels of electrons inside become more widely spaced, shifting the light emission toward blue. Larger dots emit redder light. This precise tunability makes quantum dots ideal for display technologies. Samsung, Sony, and other manufacturers now use them in QLED televisions to produce richer, more accurate colors while consuming less power. Beyond displays, quantum dots have found applications in solar cells, where they can be tuned to absorb specific wavelengths of light, potentially exceeding the theoretical efficiency limits of traditional cells. In medicine, they're used as fluorescent tag for biological imaging, allowing researchers to track molecules, cells, and tissues with unprecedented precision. Perhaps most exciting is their potential role in quantum computing. Quantum dots can trap individual electrons whose quantum states, like spin, can serve as qubits, the fundamental units of quantum information. Unlike some other qubit technologies, quantum dot qubits potentially offer the perfect combination of controllability, scalability, and the ability to operate at higher temperatures. Despite their promise, quantum dots face challenges. Some contain toxic elements like cadmium, though researchers are developing safer alternatives. Their quantum properties can be affected by their surface chemistry and environment, requiring careful engineering for consistent performance. The story of quantum dots exemplifies how fundamental research can lead to unexpected applications. They were first theoretically described in the 1970s and created in the 1980s, but few predicted their impact on consumer electronics and biotechnology. Today, they're a multi-billion-dollar industry and a cornerstone of nanotechnology. Quantum dots are the perfect example of quantum effects becoming visible at the nanoscale. They're not just scientifically fascinating, they're becoming part of our everyday technology. As you drift towards sleep, consider that quantum dots might be illuminating your room right now if you own a newer television. Tiny quantum systems engineered to produce the perfect colors for your viewing pleasure. Quantum physics made visible through human ingenuity. Quantum thermodynamics thermodynamics. The laws of thermodynamics, developed in the 19th century to understand steam engines and industrial processes, seem far removed from the quantum realm of electrons and atoms. Yet in recent decades, scientists have discovered that heat, work, and energy take on fascinating new dimensions when examined through the lens of quantum mechanics, giving birth to the field of quantum thermodynamics. Classical thermodynamics deals with macroscopic systems containing enormous numbers of particles. It tells us heat naturally flows from hot to cold objects, that perpetual motion machines are impossible, and that entropy, roughly disorder, tends to increase over time. These principles have proven remarkably robust, underpinning everything from refrigerators to rocket engines. But what happens when we scale down to quantum systems with just a handful of particles? Here, the clean boundaries between system and environment, heat and work, become blurred by quantum effects like superposition, entanglement, and measurement. Classical thermodynamics is about averages over many particles. Quantum thermodynamics asks what happens when fluctuations become as important as averages, when the statistical assumptions of classical thermodynamics break down. At the quantum scale, surprising things happen. Entanglement between particles can create quantum refrigerators that cool systems more efficiently than classical methods. Quantum coherence, the wave-like property of quantum systems, can be harnessed to extract work, suggesting new kinds of quantum heat engines with potentially greater efficiency. Perhaps most intriguingly, the arrow of time, the universal tendency for systems to evolve from ordered to disordered states, becomes more complex in quantum systems. Recent experiments have shown that under certain quantum conditions, entropy can temporarily decrease, seeming to reverse thermodynamic time. These quantum time reversals don't violate the second law of thermodynamics, but they reveal subtleties invisible in classical systems. Quantum thermodynamics may also help resolve long-standing puzzles in physics. The black hole information paradox, where information seemingly disappears inside black holes, violating quantum rules, might be resolved through quantum thermodynamic principles that preserve information in unexpected ways. Practical applications are emerging too. Quantum thermodynamic concepts are informing the design of quantum computers, which must manage heat dissipation at the quantum level. They're also guiding development of quantum sensors that exploit thermodynamic principles to achieve unprecedented sensitivity. Some researchers even suggest quantum thermodynamics might help explain life itself. Living systems maintain local order, decreasing entropy by consuming energy and producing waste heat. Quantum coherence in processes like photosynthesis might contribute to this remarkable thermodynamic balancing act. Where quantum mechanics meets thermodynamics, we find new rules for energy and information. It's forcing us to revisit foundations of physics we thought were settled over a century ago. As you rest tonight, consider that the gentle flow of heat from your body to the cooler air around you follows principles that, at the quantum level, reveal surprising subtleties and possibilities beyond what the pioneers of thermodynamics could have imagined. Dirac equation. In 1928, British physicist Paul Dirac achieved something remarkable. He united quantum mechanics with Einstein's special relativity in a single beautiful equation. The Dirac equation not only correctly described the behavior of electrons moving at near light speed, but also predicted the existence of antimatter before it was experimentally discovered. Many physicists consider it among the most elegant and profound equations in all of science. Previous attempts to merge quantum mechanics with relativity had encountered serious problems. Schrödinger's equation, while brilliantly successful for slower particles, failed for particles moving close to light speed. It didn't account for Einstein's insight that energy and mass are interchangeable, and it predicted probabilities greater than 100% in some relativistic scenarios, a clear sign something was wrong. My equation was more intelligent than I was, Dirac later remarked, highlighting how the mathematics revealed deeper physical truths than he initially anticipated. Unlike Schrödinger's equation, which described quantum particles with a single complex number at each point in space, Dirac's equation required four complex numbers, a four-component object called a spinor. This mathematical structure naturally incorporated electron spin, a quantum property previously added artificially to quantum theory. Most famously, the Dirac equation predicted that every particle should have a corresponding antiparticle with identical mass but opposite charge. When Dirac first obtained this result, he was puzzled. No such particles were known. He initially suggested these might be protons, but later realized they represented something entirely new. In 1932, Carl Anderson discovered the positron, the electron's antiparticle, confirming Dirac's prediction and earning him a Nobel Prize. The equation's implications went further. It showed that empty space isn't truly empty, but filled with a sea of negative energy electron states. When one of these electrons is excited to a positive energy state, it leaves a hole in the sea, what we observe as a positron. This revolutionary picture foreshadowed the development of quantum field theory, where particles are viewed as excitations in underlying fields. Beyond antimatter, the Dirac equation explained the fine structure of atomic spectra, predicted quantum relativistic effects, like a rapid oscillatory motion of elementary particles, and laid groundwork for understanding phenomena like vacuum polarization. Today, the Dirac equation remains central to particle physics, quantum field theory, and even practical applications like relativistic calculations in chemistry, which are essential for understanding heavy elements and their properties. The equation is a work of art. It achieves great physical insight with mathematical elegance and economy of means. As you close your eyes, reflect on how Dirac's mathematical insight revealed antimatter, an entire mirror image of the physical world, existing alongside us, testament to the profound truths mathematics can uncover about our universe. Quantum constant. The quantum world is governed by several fundamental constants, specific numerical values that seem arbitrary, yet determine the basic fabric of reality. These constants aren't derived from theory, they must be measured experimentally. Their precise values make our universe what it is, and if they were even slightly different, atoms, stars, and life itself might be impossible. Perhaps the most famous quantum constant is Planck's constant, approximately 6.6 times 10 to the negative 34th joule second. First introduced by Max Planck in 1900 to explain blackbody radiation. This tiny value defines the fundamental granularity of the quantum world. It appears in countless quantum formulas, from the uncertainty principle to the Schrödinger equation, and essentially determines the boundary between quantum and classical behavior. Planck's constant is not just another measurement. It represents nature's fundamental limitation on what can be known. It sets the scale at which quantum effects become important. Often physicists use the reduced Planck constant, which equals Planck's constant divided by 2 times pi. This simplifies many important equations, including the uncertainty principle. Another crucial quantum constant is the elementary charge, the magnitude of the electric charge carried by a single electron or proton, approximately 1.6 times 10 to the negative 19th coulombs. This fundamental unit determines the strength of electromagnetic interactions at all scales, from chemical bonds to light emission. The electron mass, approximately 9.1 times 10 to the negative 31st kilograms, is another essential constant. Combined with Planck's constant and the elementary charge, it determines the Bohr radius, the approximate size of atoms, and influences countless other atomic properties. Less discussed but equally important is the fine structure constant, approximately 1 divided by 137. This dimensionless number describes the strength of the electromagnetic force and appears throughout quantum electrodynamics. Richard Feynman called it one of the greatest mysteries of physics because no one knows why it takes this specific value. Yet, if it were just slightly different, stable atoms couldn't form. Some constants, like The Josephson constant and von Klitzing constant are so precisely measurable that they've become the basis for defining other units. Since 2019, the kilogram has been defined using Planck's constant rather than a physical reference object. Intriguingly, some theories suggest these constants might not be constant across all time and space. Slight variations could exist in different regions of the universe or have changed over billions of years. Detecting such variations would revolutionize our understanding of physics. These constants represent the universe's fundamental setting. They're the numbers that make reality what it is, rather than something completely different. As you drift towards sleep, consider that the precise dance of atoms in your body, the chemistry that enables your thoughts, and even the stars visible through your window are all calibrated by these specific quantum values, cosmic settings that make our universe uniquely habitable. The quantum gravity problem. For nearly a century, physicists have sought the ultimate theory, one that unifies quantum mechanics with Einstein's general relativity. This elusive quantum gravity would describe everything from subatomic particles to black holes and the Big Bang itself. Despite being perhaps the most significant unsolved problem in theoretical physics, we've made tantalizing progress that suggests several possible paths forward. The challenge is formidable because quantum mechanics and general relativity describe reality in fundamentally different ways. Quantum theory portrays the world as discrete, probabilistic, and filled with fluctuations, while general relativity depicts gravity as the smooth curvature of space-time caused by mass and energy. These frameworks work brilliantly in their separate domains, but contradict each other at extremes like black hole interiors or the first moments of the universe. Quantum mechanics and general relativity are both incredibly successful theories. The problem is, they refuse to talk to each other. Several approaches have emerged to bridge this divide. String theory proposes that fundamental particles are actually tiny vibrating strings in higher dimensional space. Different vibration patterns create different particles, and one vibration corresponds to a graviton, the hypothetical particle carrying gravitational force. While mathematically elegant, string theory requires extra dimensions and has proven difficult to test experimentally. Loop quantum gravity takes a different approach, suggesting that space itself has a discrete quantum structure, a complex network of tiny loops woven together at the Planck scale, about 10 to the negative 35th meters. Rather than existing on a space-time background, the theory proposes that space-time emerges from these quantum relationships. Other contenders include causal set theory, asymptotic safety, and emergent gravity models. Each offers unique insights but faces significant challenges. These approaches have yielded intriguing predictions. Loop quantum gravity suggests the Big Bang might actually be a big bounce, with a previous universe contracting to a quantum state before expanding again. String theory predicts cosmic strings, enormous one-dimensional defects that might be detectable through gravitational waves. Various models suggest modifications to gravity at very large or small scales that could explain dark energy or dark matter. Experimentally testing quantum gravity is extraordinarily difficult, as its effects typically become significant only at energies far beyond what particle accelerators can reach. However, astronomers might detect quantum gravity signatures in cosmic rays, gravitational waves, or the cosmic microwave background radiation, the afterglow of the Big Bang. Quantum gravity isn't just an academic puzzle. It's essential for understanding the beginning of the universe, what happens inside black holes, and ultimately the complete structure of reality. While a complete theory remains elusive, each approach to quantum gravity has expanded our mathematical understanding and conceptual framework, gradually illuminating what Einstein called the edge of darkness. The quest continues, driven by the conviction that at the deepest level, nature must be consistent, even if our theories are not yet. As you drift off to sleep, Imagine the fabric of space-time around you, which appears so smooth and continuous, might at the smallest scales be woven from quantum thread, a cosmic tapestry whose pattern we're still striving to discern. The black hole information paradox. What happens to information that falls into a black hole? This seemingly simple question has developed into one of physics' most profound paradoxes, pitting the principles of quantum mechanics against general relativity and challenging our understanding of reality's most fundamental aspects. According to quantum mechanics, information cannot be destroyed. The complete quantum state of a system always evolves in a way that theoretically allows you to reconstruct its past state. Information is conserved. But this principle appears to clash directly with black holes. Stephen Hawking's groundbreaking work in the 1970s showed that black holes actually emit radiation, now called Hawking radiation. This occurs when quantum fluctuations near the event horizon create pairs of particles, one falling in, one escaping. Over time, this process causes black holes to evaporate completely. If you throw something into a black hole, that information seems lost forever, Hawking initially concluded. But quantum mechanics forbids information loss. This creates a paradox at the heart of physics. Here's the problem. Hawking radiation appears completely thermal and random, carrying no information about what fell into the black hole. When the black hole eventually evaporates, all the information about the objects that fell in seems permanently erased, directly violating quantum principles. This paradox has spawned numerous proposed resolutions. One suggests that information might be stored in subtle quantum correlations within the Hawking radiation, encoded in a way we don't yet understand. Another proposes that information is preserved in a holographic imprint on the event horizon. More radical solutions include the possibility that information escapes into parallel universes, or that firewalls at the event horizon prevent information from entering black holes in the first place. In 2019, Hawking's longtime collaborator Don Page and colleagues proposed that black holes might have soft hair, subtle quantum gravitational effects at the horizon that store information. Meanwhile, some string theorists believe the paradox is resolved through the holographic principle, where information in a volume of space can be encoded on its boundary. The stakes are enormous. This isn't just about black holes. It's about whether quantum mechanics is correct, whether information is truly conserved, and ultimately about the nature of reality itself. Recent developments have tied the paradox to another profound concept, quantum entanglement. Some theories suggest black holes are maximally entangled with their own radiation, preserving information through quantum correlations across the event horizon. This paradox represents the perfect storm where our most successful theories collide, revealing the urgent need for a quantum theory of gravity. Its resolution may require a conceptual revolution comparable to those initiated by Einstein and the quantum pioneers. When quantum mechanics meets black holes, we glimpse the deepest structure of reality. The paradox isn't just a problem, it's an opportunity to discover the fundamental architecture of our universe. As you contemplate sleep, consider that the resolution to this paradox might not just change our understanding of black holes, but transform our conception of space, time, and information at the most fundamental level. Quantum criticality. At the boundary between different phases of matter lies a fascinating regime called quantum criticality, a place where quantum fluctuations dominate across all length scales, creating emergent phenomena that challenge our understanding of many particle systems. This isn't just an exotic curiosity. Quantum critical points may hold the key to understanding some of the most puzzling materials in condensed matter physics, from high-temperature superconductors to strange metal. In classical physics, matter undergoes phase transitions at specific temperatures. Water freezes at 0 degrees Celsius or boils at 100 degrees. These transitions are driven by thermal fluctuation. But what happens when we approach absolute zero, where thermal fluctuations cease? Rather than becoming simple and quiet, certain materials reach quantum critical points where quantum fluctuations extend across all scales, creating extraordinary behaviors. Quantum criticality is like a storm at the boundary between different phases of quantum matter. It creates turbulence in the quantum field that can lead to entirely new phenomena. Near quantum critical points, a material's properties become universal, meaning they follow mathematical patterns independent of the specific material. Time and space become strangely connected, with quantum fluctuations showing self-similar patterns across different scales, a property called quantum scale invariance. One of the most striking features of quantum critical systems is how they defy standard models of metals. In ordinary metals, electrons behave as almost free particles, occasionally scattering off impurities or each other. But in strange metals near quantum critical points, this picture breaks down completely. Electrons become so strongly correlated that they lose their individual identities, creating entirely new collective behaviors. These strange metals show unusual electrical resistance that scales linearly with temperature, unlike conventional metals where resistance typically follows a quadratic relationship. This linear in temperature resistivity appears in materials like high-temperature superconductors just above their transition temperature, suggesting quantum criticality may be essential to understanding these technologically important materials. Even more exotic is the potential connection between quantum criticality and emerging space-time. Some theoretical approaches, particularly the correspondence from string theory, suggest that quantum critical behavior can be mathematically mapped to gravitational systems in higher dimensions. This hints at a deep connection between quantum criticality and the nature of space-time itself. Experimentally, quantum critical points have been observed in various materials, from certain heavy fermion compounds to layered copper oxides. By applying pressure, magnetic fields, or chemical doping, researchers can tune materials to these special quantum boundary conditions. Quantum criticality reminds us that the quantum world isn't just about individual particles. It's about how countless particles organize themselves into states of matter that transcend the behavior of their constituents. As you drift asleep, imagine the electrons in various materials around you, some flowing freely as in metals, others locked in place as in insulators, and perhaps some hovering at the mysterious boundary of quantum criticality, where conventional descriptions break down and new physics emerges. Quantum simulation. Some quantum systems are so complex that even our most powerful supercomputers struggle to simulate them. A hydrogen molecule? No problem. But add just a few more atoms, and the computational requirements explode exponentially. This limitation inspired physicist Richard Feynman's revolutionary insight in 1982. Perhaps we could use quantum systems themselves to simulate other quantum systems. This idea, quantum simulation, has grown into a major field, driving both fundamental science and practical application. Unlike conventional computer simulations that approximate quantum behavior with classical calculation, quantum simulators harness actual quantum effects like superposition and entanglement to directly model quantum systems. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical, Feynman famously declared. He recognized that quantum systems could potentially perform calculations exponentially faster than classical computers for certain problems. Today, scientists pursue two main approaches to quantum simulation. Analog quantum simulators are purpose-built quantum systems specifically designed to mimic another quantum system of interest. For example, arrays of ultra-cold atoms trapped in optical lattices, patterns created by intersecting laser beams, can simulate the behavior of electrons in solid materials. These systems act as quantum model trains, providing insights into phenomena like superconductivity, magnetism, and phase transitions that would be computationally intractable on classical computers. Digital quantum simulators, by contrast, are more flexible quantum computers that can be programmed to simulate various quantum systems. Though currently limited by the number of qubits and error rates, these devices show promise for eventually simulating complex molecular structures, potentially revolutionizing drug discovery and materials science. Quantum simulations have already achieved impressive results. In 2017, researchers used a 51-qubit quantum simulator to model quantum magnetism beyond what classical supercomputers could handle. Others have simulated exotic states of matter like time crystals, systems that exhibit temporal order in their dynamics, and topological phases that might someday enable fault-tolerant quantum computing. Perhaps the most tantalizing application is simulating molecules for drug discovery and materials design. Accurately modeling how electrons behave in complex molecules could allow scientists to identify promising pharmaceuticals or catalysts without expensive trial and error experimentation. Quantum simulations could reveal the exact folding patterns of proteins or help design room-temperature superconductors that would revolutionize energy transmission. Beyond practical applications, quantum simulators serve as experimental platforms to test fundamental physics. They allow scientists to create and study quantum states that don't naturally occur, probe the boundaries between quantum and classical behavior, and explore exotic phenomena like many-body localization or quantum phase transition. The field faces significant challenges. Controlling quantum systems while shielding them from environmental disturbance requires extraordinary precision. Current quantum simulators still have limited size and fidelity. Nevertheless, they're already tackling problems beyond classical capabilities, occupying a sweet spot where they outperform classical computers but remain feasible to build with current technology. As you drift towards sleep, consider that somewhere in a laboratory, artificial quantum systems are being engineered to mimic the very atomic and molecular processes occurring throughout your body. These quantum imitations of nature may someday help us understand everything from photosynthesis to consciousness itself, all building on Feynman's insight that the best way to understand quantum reality is with quantum systems themselves. Quantum random number generators. The flip of a coin, the roll of a dice, the shuffling of cards. Humans have long sought ways to generate randomness. But are these methods truly random? Not really. Classical randomness is merely apparent randomness arising from complexity. If you knew the exact force applied to the coin, the air currents present, and other variables, you could theoretically predict the outcome. True randomness, events with absolutely unpredictable outcomes, seemed philosophically impossible. Then quantum mechanics changed everything. Here was a theory suggesting that certain events, like the decay of a radioactive atom or the path of a photon through a beam splitter, are fundamentally random. Not just random because we lack information, but random in the deepest possible sense. Even nature itself doesn't know the outcome until it happens. This intrinsic randomness, so philosophically troubling to Einstein when he declared that God does not play dice with the universe, has become a technological resource through quantum random number generators. Unlike algorithmic random number generators used in classical computers, which produce sequences that appear random but are actually predetermined, quantum random number generators tap into the inherent unpredictability of quantum processes to create numbers that are provably random. The simplest quantum random number generator might send single photons toward a half-silvered mirror. Each photon either passes through or reflects with equal probability, creating a random sequence of ones and zeros. More sophisticated devices exploit quantum fluctuations in vacuum, the timing of radioactive decay events, or the quantum noise in electronic components. Why does true randomness matter? For cryptography, truly random keys are essential for unbreakable encryption. Many cryptographic systems have been compromised not because their algorithms were broken, but because their random number generators were predictable. Quantum random number generators eliminate this vulnerability. Beyond security, random numbers are vital in scientific simulation, statistical sampling, fairness in gaming and lotteries, and even artistic endeavors. Some online services now offer access to quantum-generated randomness, and commercial quantum random number generators have become available to consumers. Perhaps most intriguing is the philosophical implication. Quantum random number generators provide strong evidence that true randomness exists in nature. Each quantum random bit represents a tiny decision point where the universe genuinely could have gone either way, not because of our ignorance, but because both possibilities were real until the moment of quantum measurement. As you close your eyes tonight, consider that in quantum random number generators, we've created devices that harness nature's inherent unpredictability, turning what Einstein considered a flaw in quantum theory into a practical technology that provides something impossible in a purely classical world, numbers that no one, not even nature itself, could have predicted in advance. Quantum metrology. How precisely can we measure physical quantity? This seemingly simple question leads us into the fascinating realm of quantum metrology, the science of achieving the highest possible precision in measurements by exploiting quantum effects. Classical measurement precision is fundamentally limited by statistical fluctuation. If you're counting discrete events, like photons hitting a detector, the uncertainty typically scales as 1 divided by the square root of the number of events. This is the standard quantum limit, and for decades it was considered an insurmountable boundary. But quantum mechanics, so often seen as introducing uncertainty through principles like Heisenberg's uncertainty relation, can actually be harnessed to overcome these limits. By using quantum resources like entanglement and superposition, quantum metrology pushes measurement precision beyond what classical physics allowed. Consider measuring the phase of light. Classical approaches, using even the best laser sources, can only achieve precision at the standard quantum limit. But by using squeezed light, where quantum uncertainty is redistributed, reducing fluctuations in one property at the expense of another, physicists have demonstrated measurements that break this limit. Even more powerful are approaches using entangled particles, where quantum correlations between particles are exploited to achieve what's called Heisenberg limited sensing, the ultimate precision allowed by quantum mechanics. This represents a quadratic improvement over the standard quantum limit, meaning measurements become dramatically more precise as the number of particles increases. These aren't just laboratory curiosities. Quantum metrology is finding applications in fields ranging from gravitational wave detection to biological imaging. The advanced LIGO observatories, which first detected gravitational waves in 2015, use squeezed light to enhance their sensitivity to tiny space-time ripples. Meanwhile, quantum-enhanced microscopes can image delicate biological samples with unprecedented clarity while using lower light intensities that prevent damage to the specimen. Perhaps the most practical current applications are in timekeeping. Quantum metrology enables atomic clocks so precise they would neither gain nor lose a second in billions of years. These clocks are sensitive enough to detect relativistic time dilation from a height difference of just a few centimeters in Earth's gravitational field. The field is advancing rapidly. Researchers are developing quantum sensors capable of detecting minute magnetic fields from brain activity, precisely mapping gravitational anomalies to locate resources underground, and creating gyroscopes sensitive enough to track movement without GPS. What makes quantum metrology particularly powerful is how it turns quantum weirdness, the very features that make quantum mechanics seem so counterintuitive, into practical advantage. Entanglement, often viewed as quantum mechanics' most peculiar feature, becomes a resource that can be harvested for unprecedented measurement precision. As you drift towards sleep, consider that the quest to measure our world with ever greater precision isn't just about better technology. It's a journey toward the fundamental limits of knowledge itself, boundaries set by the quantum nature of reality that we're now learning to approach through the clever exploitation of quantum effects. Quantum optics. Light, the most familiar form of electromagnetic radiation, takes on extraordinary properties when examined through the lens of quantum mechanics. The field of quantum optics explores these properties, revealing light's particle-like behavior as photons, while also exploiting its wave nature to create states of light with no classical equivalent. The birth of quantum optics is often traced to Einstein's 1905 paper on the photoelectric effect, where he proposed that light consists of discrete quanta, what we now call photon. This revolutionary idea helped launch quantum mechanics and earned Einstein the Nobel Prize. Yet the full development of quantum optics awaited later technological advances, particularly the invention of the laser in 1960, which provided an intense, coherent light source ideal for quantum experiment. With lasers, scientists could create and manipulate special quantum states of light. Consider the photon anti-bunching effect, where photons in certain light sources tend to arrive one at a time rather than in bunches, a distinctly non-classical behavior that definitively demonstrates light's particle nature. Or photon indistinguishability, where two photons from the same source become essentially identical particles, exhibiting interference effects when they meet. Perhaps most fascinating are non-classical light states, like squeezed light, where quantum uncertainty is redistributed between complementary properties like phase and amplitude. Imagine squeezing a balloon. If you compress it in one direction, it bulges in another. Similarly, squeezed light reduces fluctuations in one property below what's classically possible, while increasing them in another, maintaining the overall uncertainty required by quantum mechanics. Even more exotic are Fock state, with precisely defined photon numbers, and Schrödinger cat state, where light exists in a superposition of two macroscopically distinct states, akin to the famous thought experiment where a cat is simultaneously alive and dead. Quantum optics has proven remarkably fruitful for both fundamental science and application. It provides some of our cleanest tests of quantum mechanics, as photons interact weakly with their environment and maintain quantum coherence over long distances. Practically, quantum optical systems form the backbone of many quantum technologies. Quantum cryptography uses single photons to establish unbreakable encryption keys. Quantum computers increasingly rely on photonic qubits, which can operate at room temperature and interface naturally with quantum communication systems. Meanwhile, quantum imaging techniques exploit quantum correlations between photons to achieve resolution beyond classical limits. The quantum nature of light also surfaces in surprising places, from the efficiency of photosynthesis to the precision of gravitational wave detectors like LIGO, which use squeezed light to enhance sensitivity. Recent advances include the development of integrated photonic circuits that manipulate single photons on silicon chips, and topological photonics, where light follows protected paths immune to certain types of disruption. As you close your eyes tonight, consider the photons that entered them during the day. Each one represented a tiny packet of quantum energy, governed by probability waves that spread through space, yet somehow arrived as discrete particles in your retina, a daily reminder of the quantum world's beautiful strangeness. Quantum electrodynamics. If you could choose just one physical theory to epitomize the triumph of human intellect, quantum electrodynamics, or QED, would be a strong contender. Developed primarily in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, QED describes how light and matter interact at the quantum level with astonishing precision, making it possibly the most accurately tested theory in scientific history. QED merges quantum mechanics with Einstein's special relativity to describe electromagnetic interaction. It views these interactions as occurring through the exchange of virtual photons, force-carrying particles that pop in and out of existence too quickly to be directly observed. When two electrons repel each other, for instance, they're essentially throwing photons back and forth, like people in boats tossing balls to push away from each other. What makes QED remarkable is its mathematical approach. Feynman developed a visual shorthand called Feynman diagrams to represent particle interaction. Each diagram represents a term in a complicated mathematical expansion, with simpler diagrams giving the largest contributions and increasingly complex diagrams providing progressively smaller corrections. The theory makes predictions that match experimental measurements to an extraordinary degree. The most famous example involves the magnetic properties of electrons. QED predicts the electron's G factor, essentially how strongly it responds to magnetic magnetic field, with an accuracy equivalent to measuring the distance between New York and Los Angeles to the width of a human hair. Despite this incredible success, calculating with QED isn't straightforward. The theory initially produced infinite answers for certain quantities, a problem physicists solved through the process of renormalization, essentially redefining parameters to absorb these infinities. While mathematically sound, this approach troubled even Feynman, who called it a dippy process despite having helped develop it. QED serves as the template for other quantum field theories, including quantum chromodynamics, which describes the strong nuclear force, and electroweak theory, covering weak nuclear interaction. Together with these theories, it forms the standard model of particle physics, our most comprehensive description of fundamental particles and forces, excluding gravity. Beyond its theoretical elegance, QED explains countless physical phenomena. It accounts for the spontaneous emission of light from excited atoms, the Lamb shift in atomic spectra, and the Casimir effect, where quantum fluctuations create a force between uncharged plates. The lasers in your devices, the LED lights in your home, and the touchscreen on your phone all function according to QED principles. QED reminds us that what seems like empty space is actually a seething quantum vacuum full of virtual particles popping in and out of existence, a modern echo of Aristotle's ancient claim that nature abhors a vacuum, though for reasons he could never have imagined. As you drift toward sleep, consider that the apparently simple process of seeing photons interacting with electrons in your retina involves quantum field processes of such mathematical intricacy that understanding them represents one of humanity's greatest intellectual achievements, all while nature performs these calculations effortlessly quintillions of times every second. The Heisenberg picture. When physicists describe how quantum systems evolve over time, they typically use one of two mathematical frameworks, the Schrödinger picture or the Heisenberg picture. While they're mathematically equivalent, giving identical predictions for experiments, they offer profoundly different perspectives on what's changing in a quantum system. In the more commonly taught Schrödinger picture, quantum states evolve over time, while operators representing observable quantities remain fixed. This matches our intuition. The physical system changes while our measuring devices stay the same. When an electron moves, we think of the electron's quantum state changing, while the position operator that measures it remains constant. The Heisenberg picture, developed by Werner Heisenberg in 1925, flips this perspective. Here, the quantum state remains fixed, while the operators evolve over time. Rather than the electron moving, it's as if the coordinate system itself is changing, redefining what position means at each moment. This seemingly backwards approach actually connects more naturally with classical physics, where physical variables like position and momentum evolve while the state of the system remains conceptually fixed. The shift between these pictures involves more than mathematical convenience. It reveals deep insights about quantum reality. In the Heisenberg picture, the time evolution of operators directly reveals the connections between different physical quantities through what are called commutation relations. These mathematical relationships encode the uncertainty principle and other distinctly quantum features. Heisenberg's approach proved particularly valuable for quantum field theory, where it's often more natural to track how field operators change than to follow the enormously complex quantum state of the entire field. It also connects elegantly to symmetry principles through Noether's theorem, which relates conserved quantities like energy and momentum to symmetries in physical laws. One striking advantage of the Heisenberg picture emerges when dealing with systems that don't change over time, what physicists call equilibrium state. In such cases, the state remains constant even in the Schrödinger picture, but the correlations between measurements at different times become clearly visible through the evolution of operators in the Heisenberg picture. For computational purposes, physicists often use a hybrid approach called the interaction picture, where both with states and operators evolve partially. This divides the problem into a simple part that can be solved exactly and a complex interaction that requires approximation technique. The existence of these equivalent pictures highlights something profound about quantum mechanics. The line between what we consider the system and how we measure it is ultimately arbitrary. We can place the time dependence in either the states or the measurement operators and get identical physical predictions. As you relax into sleep, consider this remarkable feature of quantum theory, that it allows multiple mathematically equivalent viewpoints, like different languages expressing the same underlying reality. The quantum world doesn't care whether we use Schrödinger's or Heisenberg's approach. It simply unfolds according to its own rule, while we create various mathematical lenses through which to understand it. Topological quantum computing. Imagine building a quantum computer where information is stored not in the fragile states of individual particles, but in the collective topological properties of a system. Properties so robust they remain unchanged even when the system is disturbed. This is the promise of topological quantum computing, an approach that could potentially overcome the greatest challenge facing quantum computers: decoherence and errors. Conventional quantum computing faces a fundamental difficulty. Quantum states are incredibly delicate. Environmental noise easily destroys quantum coherence, and even slight perturbations can corrupt quantum information. Elaborate error correction schemes exist, but they require many physical qubits to protect a single logical qubit, making scaling up extremely challenging. Topological quantum computing takes a radically different approach. Inspired by a branch of mathematics called topology, the study of properties that remain unchanged under continuous deformation. In topology, a coffee mug and a donut are equivalent because both have exactly one hole. You can reshape one into the other without tearing or gluing. Similarly, topological quantum computing encodes information in special quantum states whose essential properties are protected by topology. The key players in this approach are exotic quantum particles called anyons, quasi-particles that can emerge in certain two-dimensional systems. Unlike familiar particles like electrons or photons, anyons remember their history, specifically how they've moved around each other. Imagine anyons as dancers on a stage. What matters isn't their exact position, but the pattern of how they've woven around each other, their braiding history. This history is preserved even if the dancers' exact paths are slightly perturbed, as long as the overall braiding pattern remains the same. Computing with anyons involves creating, moving, and braiding them in specific patterns. These braiding patterns implement quantum operations, with the final state of the system representing the computation result. Because the information is encoded topologically, local disturbances don't affect the computation. They don't change the braiding history. Microsoft has made topological quantum computing central to its quantum strategy, focusing on exotic quasi-particles called Majorana zero modes that might exist at the ends of specialized nanowires. These particles, first predicted in 1937 by Ettore Majorana, have the unusual property of being their own antiparticles. When combined with superconductivity and controlled carefully, they could potentially serve as topologically protected qubits. While the theory is elegant, experimental realization remains challenging. The required exotic quantum states typically emerge only under extreme conditions. Temperatures near absolute zero and strong magnetic field. Conclusively detecting and manipulating anyone requires extraordinary precision. Nevertheless, the potential reward is immense. A quantum computer inherently protected from errors at the hardware level, requiring far fewer physical resources for reliable computation. Such a system could potentially solve problems currently considered intractable, from simulating complex quantum materials to factoring large numbers relevant to cryptography. As you drift towards sleep, consider this remarkable possibility that the future of computing might rely not on ever smaller transistors, but on the abstract mathematical properties of how exotic quantum particles dance around each other, their movements inscribing calculations protected by the very fabric of topology itself. Quantum walks. Imagine a drunk person taking random steps left or right along a path. This classic random walk has applications from modeling financial financial markets to describing particle diffusion. Now imagine a quantum version where the walker exists in a superposition of positions, with different paths interfering like waves. This quantum walk behaves dramatically differently from its classical counterpart, spreading quadratically faster and exploring multiple paths simultaneously. Quantum walks come in two main varieties. In discrete time quantum walks, the walker takes steps at distinct moments, with a quantum coin flip determining the direction of each step. In continuous time quantum walks, the evolution happens smoothly without discrete steps. Both exhibit the distinctive quantum property of interference, where probability amplitudes can enhance or cancel each other. This interference creates striking differences from classical random walk. While a classical random walker's average position remains at the starting point, with a spread proportional to the square root of time, a quantum walker's probability distribution develops complex patterns with multiple peaks spreading linearly with time, a quadratic speedup. Beyond their theoretical interest, quantum walks form the basis for quantum algorithms that outperform their classical counterpart. They provide a framework for tackling problems from database searching to graph analysis. For instance, a quantum walk can find an item in an unsorted database quadratically faster than any classical algorithm and can traverse certain network structures exponentially faster. Quantum walks have been experimentally implemented in various physical systems: photons walking through optical networks, atoms traversing laser lattices, and electrons hopping between quantum dots. Each implementation brings its own advantages and challenges, contributing to both fundamental understanding and practical application. The concept connects deeply to other quantum phenomena. Quantum walks describe the coherent transport of energy in photosynthetic complexes, where nature seems to have evolved to exploit quantum effects for efficient energy transfer. They also relate to Anderson localization, where quantum interference can cause particles to become trapped in disordered materials instead of diffusing. As a computational model, quantum walks provide an alternative framework for quantum computing, equivalent in power to the standard circuit model, but offering different intuition. Some researchers develop algorithms directly as quantum walk, finding solutions that might be less obvious in other frameworks. The boundary between quantum and classical behavior emerges naturally in quantum walk. As environmental interactions increase, causing decoherence, quantum walks gradually lose their interference patterns and quadratic speedup, eventually behaving like classical random walk. This transition offers insights into the quantum to classical boundary more generally. As you close your eyes, imagine quantum walkers traversing paths through the neural networks of your brain, their wave-like behavior exemplifying how quantum mechanics pervades even the most complex systems, following multiple paths simultaneously through the landscape of possibility before collapsing into the singular reality of your next thought. Quantum game. What happens when game theory, the mathematical study of strategic decision-making, meets quantum mechanics? The result is quantum game theory, a field that examines how games change when players can make quantum moves using superposition, entanglement, and interference as strategic resources. Consider the classic prisoner's dilemma, where two suspects must decide whether to cooperate with each other or betray each other without communication. Classically, although mutual cooperation yields the best collective outcome, rational self-interest drives both players to betray each other, leading to a worse outcome for both, a frustrating paradox of rationality. In the quantum version, players can make quantum moves that exist in superpositions of cooperate and betray. Remarkably, when the game is fully quantized and players have access to certain quantum strategies, they can escape the classical dilemma. The quantum version allows for a new Nash equilibrium, a situation where neither player can benefit by changing strategy that corresponds to mutual cooperation. This isn't just a mathematical curiosity. Quantum games provide insights into both quantum information science and evolutionary dynamics. They help us understand how quantum resources like entanglement can be leveraged for advantage in competitive and cooperative scenarios. Beyond modified classical games, entirely new quantum games have emerged. In quantum pseudo-telepathy games, players who share entangled particles can accomplish tasks that would be impossible with classical resources alone, appearing to communicate telepathically, although no actual communication occurs. The Mermin Perez Magic Square game demonstrates this dramatically. Entangled players can win with certainty, while classical players are limited to winning at most 89% of the time. Quantum game theory extends to auctions, voting systems, and financial modeling. Quantum auctions can potentially reduce collusion among bidders. Quantum voting protocols might provide stronger privacy guarantees, and quantum approaches to finance could better capture the uncertainty principles inherent in market behavior. Experimentally, simple quantum games have been implemented using quantum optical systems, nuclear magnetic resonance, and superconducting quantum processors. As quantum computers advance, more complex quantum games become accessible for both research and potentially practical application. From a philosophical perspective, quantum games raise profound questions. They reveal that rationality itself can be context-dependent. What counts as rational behavior changes when we move from classical to quantum domains. They suggest that cooperation might emerge more naturally in systems governed by quantum rather than classical rules. Some futurists even speculate that understanding quantum game theory might prove crucial for interaction with advanced artificial intelligence systems, which could potentially exploit quantum resources for decision-making in ways humans find counterintuitive. As you drift towards sleep, imagine a world where the strategic games played in business, politics, and even personal relationships incorporate quantum principles, creating new possibilities for cooperation and coordination beyond what purely classical thinking allows. A world where the quantum nature of reality isn't just a physical fact, but a resource for solving collective challenges. Quantum Darwinism. Why does our everyday world appear so classical when the underlying physics is quantum? Why do we observe definite objects with definite properties rather than quantum superposition? Quantum Darwinism, a framework developed by physicist Wojciech Zurek, offers an elegant explanation. Our classical reality emerges through a process analogous to natural selection, where only certain quantum states survive the brutal competition to imprint themselves on the environment. The central insight of quantum Darwinism is that we never observe quantum systems directly. Instead, we gather information indirectly by intercepting fragments of the environment that have interacted with the system. When you see an apple, photons that bounced off it carry information to your eyes. When you feel it, pressure receptors in your skin report its presence. Crucially, not all quantum states leave the same imprint. Some quantum states, called pointer states, are more robust against environmental interaction. These special states can redundantly imprint their information on many environmental fragments, like multiple copies propagating through the environment. Other more fragile quantum states quickly lose their coherence through environmental interaction without leaving robust record. This natural selection of quantum states explains why we perceive a consistent classical reality. Different observers can agree on the properties of a quantum system precisely because they're all detecting the same information that has been massively replicated in the environment. It's as if nature conducts billions of tiny measurements with only the most environmentally friendly quantum states surviving to be observed. Quantum Darwinism doesn't replace decoherence theory, the established explanation for how quantum systems lose their quantum behavior through environmental interaction. Rather, it extends this framework by explaining not just why quantum systems decohere, but why multiple observers perceive the same classical reality emerging from quantum foundation. The framework makes testable predictions about the information structure of the environment around quantum systems. Rather than containing random noise, the environment should contain multiple redundant copies of specific information about the system's pointer states. Recent experiments with photons and other quantum systems have begun confirming these predictions, showing that information about quantum systems does indeed proliferate in the environment, exactly as quantum Darwinism suggests. This perspective illuminates the measurement problem in quantum mechanics from a new angle. The apparent collapse of quantum states isn't a mysterious separate process, but the natural consequence of environmental selection, amplifying certain states and suppressing others through repeated information copying. Perhaps most profoundly, quantum Darwinism suggests that objectivity itself, the bedrock of scientific observation, emerges naturally from quantum physics through environmental information transfer rather than requiring separate classical principles. As you close your eyes tonight, consider that the seemingly solid, objective world around you might be the result of a continual evolutionary process at the quantum level, where only the fittest quantum states survive the harsh environment to imprint themselves on your senses, creating the illusion of a purely classical reality from the richer quantum substrate beneath. Relativistic quantum mechanics. When quantum mechanics first emerged in the 1920s, it didn't play nicely with Einstein's special relativity, a serious problem, since both theories had strong experimental support. This tension drove the development of relativistic quantum mechanics, which attempts to describe quantum particles moving at speeds approaching the speed of light. The need for a relativistic theory became apparent from several directions. First, electrons in heavy atoms move fast enough for relativistic effects to noticeably alter atomic structure and chemical properties. Second, experiments with cosmic rays revealed new particles traveling at nearly light speed. Third, and most fundamentally, a complete theory of nature had to reconcile the probabilistic quantum world with Einstein's spacetime. The first major step came from Paul Dirac, who in 1928 formulated his eponymous equation, a relativistic version of the Schrödinger equation for electrons. Unlike earlier attempts that had serious flaws, Dirac's equation naturally incorporated electron spin and correctly predicted the magnetic properties of electrons. Most remarkably, it predicted the existence of antimatter, specifically the positron, the electron's antimatter counterpart, which was discovered 4 years later. Dirac's equation revealed something profound. Relativity and quantum mechanics together require that particles must have antimatter partners with identical mass but opposite charge. This wasn't just a mathematical curiosity, but a fundamental consequence of uniting relativity's equivalence between energy and mass with quantum mechanics' probabilistic nature. However, relativistic quantum mechanics faced serious challenges. When extended beyond single particles to interactions between particles, the mathematics frequently produced infinite results, clearly a sign that something was wrong. The framework also struggled with particle creation and annihilation, processes that occur naturally at high energies when mass and energy can transform into each other. These limitations led to the development of quantum field theory, which views particles not as fundamental objects, but as excitations in underlying quantum fields that permeate all space. This more comprehensive framework successfully addressed many problems of relativistic quantum mechanics, culminating in the standard model of particle physics. Nevertheless, relativistic quantum mechanics remains important as an intermediate framework. It correctly describes relativistic effects in atoms, explains the behavior of electrons in materials like graphene, where they obey Dirac's equation rather than Schrödinger's, and provides the foundation for understanding phenomena from spin-orbit coupling to the fine structure of atomic spectra. Relativistic effects aren't just theoretical curiosity. They directly impact our daily lives. The yellow color of gold, the liquidity of mercury at room temperature, and the stability of lead all result from relativistic effects on electron behavior. Even modern technologies like lithium-ion batteries and catalytic converters rely on materials whose properties are significantly shaped by relativistic quantum effects. As you drift towards sleep, consider that the marriage of quantum mechanics and relativity, though initially troubled, revealed antimatter, transformed our understanding of empty space, and continues to shape our technological world, while pointing toward even deeper unification still being sought at the frontiers of theoretical physics. Quantum error correction. The extreme fragility of quantum information presents one of the greatest challenges to building practical quantum computers. Qubits are notoriously sensitive. Even slight interactions with their environment cause decoherence, destroying the delicate quantum states necessary for computation. For years, this sensitivity led many to believe large-scale quantum computing might be fundamentally impossible. Then, in 1995, Peter Shor made a breakthrough discovery. Quantum error correction is possible. This revelation transformed quantum computing from a theoretical curiosity into a potentially practical technology, spawning an entire field dedicated to protecting quantum information from noise and errors. Classical error correction is straightforward. You simply make multiple copies of your data. If one copy gets corrupted, you can compare it with the others to identify and fix errors. But quantum information can't be copied due to the no-cloning theorem, a fundamental restriction in quantum mechanics. This seemed to make quantum error correction impossible. The ingenious solution leverages entanglement to spread quantum information across multiple physical qubits. Rather than making prohibited copies, quantum error correction encodes a single logical qubit across several physical qubits in such a way that the quantum information is stored in their collective quantum state. Local errors affecting individual physical qubits can then be detected and corrected without ever needing to measure the protected quantum information directly, which would destroy the quantum computation. The simplest quantum error correcting code, the 3-qubit bit flip code, encodes a single logical qubit across 3 physical qubits. If an error flips one of the physical qubit, the error can be identified and corrected by majority voting without collapsing the quantum superposition. More sophisticated codes protect against different types of errors and use more physical qubits to provide stronger protection. Among the most promising approaches are surface codes, which arrange physical qubits in a 2-dimensional lattice. These codes can tolerate relatively high error rates in the underlying physical qubits, making them practical for near-term quantum hardware. However, they require significant overhead, potentially thousands of physical qubits, to encode a single logical qubit with sufficient protection. The threshold theorem, a landmark result in quantum computing theory, proves that if physical error rates can be pushed below a certain threshold, roughly 1%, then quantum error correction allows for arbitrarily long quantum computations. This means that despite the unavoidable noise in any real quantum system, large-scale quantum computers are theoretically possible. Beyond computing, quantum error correction connects to fundamental physics. The concepts developed for protecting quantum information have found applications in understanding black hole information paradoxes, quantum gravity, and even certain exotic phases of quantum matter. Today, implementing quantum error correction represents one of the central challenges in building useful quantum computers. Each major quantum computing platform, superconducting circuits, trapped ions, photonics, spin qubits, requires specialized error correction approaches tailored to its unique error characteristic. As you relax into sleep, consider this remarkable achievement. We've found ways to protect quantum information, not by isolating it from the environment, an impossible task, but by cleverly encoding it across multiple physical systems so that the fragile quantum essence survives even when individual parts are corrupted by unavoidable noise.